Monitor's not working.
Monitor's not
It's not working.
Oh, that's okay. Yeah, that's fine.
Yeah, just a second. So I think he was going to come back later and
Fix it up. No problem. Thanks. Thank you. I think we're going to start. I think we have got a full day ahead for us, so just want to make sure that we start on time. But I would also like to wish to acknowledge the people of Kulin Nation on whose land we gather today. I pay my respect to their elders and past and present. Thank you very much for coming. Can you hear me? I do talk a bit loud, but I don't know if the other presenter is going to talk this loud. So if you want to really hear, please move in front. As I said before, it's a full day affair, but I just want to welcome you and just give you a couple of items here, what we are going to do today, and then hand over to our chairperson. So 10:15 to 10:30, very short morning tea break, because we didn't want to encroach into the presenter's time. And then at 12:30, we have got a lunch for half an hour, which lunch will be served here. And then the interesting part, physically you will go and visit a couple of innovation here happening at Monash. We call it cave and drone visits. Here you would see cave and drone visit at 12:30, sorry, 1 o'clock. We have allocated 1 hour, but we had to break you all into 3 groups because some facilities don't have they cannot really have a larger group. So at morning tea you will be hand over a small ticket with 1, 2 or 3, and then you will be part of that 1 or 2 or 3 groups, so that then we can work out how to actually arrange yourself. Afternoon tea is from 3:45 to 4, and then we plan to finish at 5. So that's the day's plan. The chairperson for this workshop is Chris McEwen. Most of you would know Chris. Chris is the Chief Investigator Transport Safety in Victoria. Chris has worked in public transport in Victoria for more than 30 years in the areas of electrical infrastructure, rolling stock and safety. We had lots of privileges to work with Chris in several projects, so I think we know Chris quite well, and we thought he will be the best person to chair this important workshop. In his previous position, Chris was the Director Rail Safety with Transport Safety Victoria, and is currently the Chief Investigator Transport Safety, an independent, multimodal, no-blame safety investigator covering maritime, rail and bus public transport in Victoria. Chris has got a master's in electrical engineering. He's a chartered professional engineer, and most importantly, he's a member of RTSA. So with that, please, I will hand over to Chris, and he will take on from this point. Chris, over to you.
Good morning, everyone. Welcome this morning. I'll try and speak loudly, so if you hear my voice a little drooping, just sort of wave your hand, and I'll try and pick it up again.
You can. I'm not.
Okay, so I've got some slides.
You've got some slides, but I'm not sure. You might have to stand here and talk. You can actually pick up. Do we have a control? You can use this microphone if you want.
Great. Okay.
And also, do you have a remote? I think there must be a remote on the other side. Just check. No, we don't have one. Okay, so you might have to use this one. Yeah. Sorry.
That's right. Okay.
Try that.
Just it? I'll hold it because I think I'll have to be handing it on to the next speaker. Okay, so I'm just going to talk a little bit about my function and about the objectives of today's workshop to start with. I won't talk about program because Ravi's already had the program up. So Chief Investigator Transport Safety. It's an independent agency established under the Transport Integration Act Victoria 2010. So we investigate rail, maritime and bus safety incidents in Victoria. So rail incidents in particular are investigated under a collaboration agreement with the Australian Transport Safety Bureau, and the reports are published with the Australian Transport Safety Bureau. So we work very closely with our federal agency. So just before I get into objectives, so in part today is a continuation of what went on last night, and so to bring people up to date a little bit on that is that Gary Wolfe, who I will be reintroducing a little bit later, talked a lot about technology. It's a little bit. Hopefully that's better. Yeah. Okay. Talked a lot about technology and possible cases for what would enable new technology to be deployed for measuring track features and rolling stock features. And in particular, the business case for doing that in the US is often linked very heavily to the safety regulations from the FRA. And so for that to be, I think it's probably a bit too echoey. I'll try this one. Yeah, that's better. So the business case is often linked, it seems, to the ability of the regulator to reduce requirements for particular inspections, and by reducing human inspections, you can save money, and that offset can pay for new technology. The trouble is that they're, as I understand it, they're legislated safety standards. So to convince the regulator that some new technology is worthy of relaxing particular safety standards is no small task. So in Australia, the situation is quite different, and so today we're going to have an opportunity to further examine some of the new technologies, and also look very carefully at the legislative safety framework that might require certain things to be done before you introduce new technology. And we're also going to look at what the role of the track managers are in terms of setting standards. So I think today is about understanding the requirements and limitations of current maintenance standards and what that means for adoption of new technology, understanding what new technology is available and how it is being used and how it might be used. And I think one of the other interesting things that came out from last night, Gary was talking about new technology, but it's really now existing proved technology that's deployed in some places, particularly mining railways in Australia and overseas, but not really being deployed in other situations. So it's really known technology, just underutilised in some cases. So, and finally, understand the requirements and implications of the National Rail Safety Law in terms of track maintenance and adoption of new technology. But I'm presuming that that will actually be broader and will enable you to get an insight into what that means for technology generally. So, at the end of the day, Ravi showed on the program, there's an opportunity for a workshop, and really it's a opportunity for you to engage with the panel and unpeel the onion that is involved in what might be implementing new technology. Okay, so that's really all I wanted to cover at this stage. So we'll get on to the first speaker. So and the first speaker is Andy Webb. I'll just introduce him. So Andy is the Senior Manager of Major Projects for the Office of National Rail Safety Regulator. He has 30 years experience in signalling maintenance, railway infrastructure, asset management and certification audits for the Victorian Government, British Rail and MTR. So Andy is a Chartered Professional Engineer and a Fellow of Engineers Australia. So welcome, Andy.
And it all works. Good. Well, thanks, Chris. Delighted to be here and delighted to be in the spotlight. That's quite a bright light. To explain a bit about the rail safety national law and its relevance to standards. I'm hoping over the next hour or just under to explain roughly what the ONRSR is about, what we cover, or the area we cover here in Australia, our organisation and function, really just to set the scene a bit. Then have a look at the Rail Safety National Law and its approach to standards, and then maybe kind of throw out a few thoughts about how we should be approaching maintenance standards, maybe some of the things we might want to think about, and ensure ultimately at the end of the day that the standards that we have support safe delivery of railway operations. Certainly interesting to know, unfortunately I wasn't here yesterday evening, but what Chris has just been talking about, the American approach, and in the US the regulator I think is far more prescriptive, but it was interesting I think just right at the very beginning to be talking about innovation and new technology, and that might be something I hope that does come out in the discussion that we have here today. Yesterday I was at another conference, and I might feel slightly nervous as a signal engineer in this particular audience, but it was far more comfortable. Yesterday I was at a train control management system conference up in Sydney, and the message from the regulator at that conference was the regulator supports the safe delivery of innovation. So if you're talking today about using new technology, I think that's a great idea. It will always be a good initiative, and if it's delivered safely, the regulator will be there to support and facilitate that change. But anyway, getting back to what I'm here to talk about. So an overview of the ONRSR, so it's the Office of the National Rail Safety Regulator, and I still find it a bit strange that it's one of the few abbreviations that's as much of a mouthful as the actual phrase, but the ONRSR is the safety regulator for railways in Australia. And in terms of history, I'm reliably informed that it was probably about 1831, I think, the first railway appeared in Australia, somewhere near Newcastle. And from that day onward, I'm sure we're all happy in the belief that someone was thinking about safety. And I presume almost at the beginning, someone might have had the bright idea of, wouldn't it be good if safety was managed consistently and coherently across the whole country? So it took until the early 90s for that thought bubble to become a bit more of a firm bubble, if that's possible. And the intent was created that we should be having a national regulator and national law. Things take a bit of time, and in 2009 governments agreed that we should have a national law and a national regulator, and the process to start that then commenced a couple of years later, and a couple of years after that, we had the ONRSR starting in January 2013. So the regulator is an independent authority. It's an independent body. It's funded by government and industry, but we are independent. We have a national office in Adelaide, where our central branch is located. We deal with industry generally through our branches, and central branch covers South Australia, Tasmania, the Northern Territories, and currently the ACT. We have a branch here in Victoria that delivers its services to ONRSR through a service level agreement with the good people within Transport Safety Victoria. In New South Wales, it's a similar arrangement where the Independent Transport Safety Regulator, ITSA, of New South Wales delivers its services to ONSA. The good news on that front is, as of this Thursday coming, next week, ITSA will cease to exist, and as of Friday next week, regulation in New South Wales will be under direct control of the ONRSR. It's a big change for us. I can tell you're as excited as we are. But ultimately, in terms of creating a national regulator, this is an important milestone. Over in Western Australia, they're directly controlled by the ONRSR too. Some of the more observant in the room might have noticed that Queensland's not quite got the same colour scheme. Queensland currently isn't part of the national regulatory approach, but they're on the verge of, and I think yesterday it was announced that Queensland Parliament's agreed to the legislation for Queensland to become part of ONRSR. So at some point this year, near as darn it, we'll have one regulator, safety regulating most railways in Australia. Who are we? We are split into a number of organisational divisions. Sue McCarry is the national regulator. Some of you may have met her or seen her around. We have a number of divisions split up like any other organisation. I think most of you, if you have any dealings with the regulator, it would be through the national operations where our branches are. So that would be the Victorian branch manager or the New South Wales branch director. So what do we do? Now, there are some key functions that the regulator performs, and these are not functions that we all sat down and thought of would be a good thing for us to do. These are functions legislated within the Rail Safety National Law. So the regulator's functions are to administer, audit and review the accreditation regime. That's the process by which railway operators are allowed to do railway operations. We have to work with rail transport operators, which will be a lot of people in the room here, and rail safety workers and others, to improve rail safety nationally, and conduct research and collect and publish information. We also provide or facilitate education and training. We're also here to monitor, investigate and enforce compliance with the law, and at times you might see some of the rail safety officers out undertaking audits and inspections. And also to engage in, promote and coordinate sharing of information relevant to rail safety, which is probably one of the reasons I'm here today. So what's our approach? And understanding our approach, I think is important to put into context the rest of the discussion that I'll be having just now and perhaps for the rest of the day. But the regulatory approach as we deal with industry is that We aim to be independent and impartial. We aim to be risk-based, where our activity should really be focused on the areas that have the highest potential for creating safety risk, or the highest potential for seeing safety improvement. Our engagements with industry, we hope, would be educational, and we feel it's also important that our engagements are, particularly with compliance and enforcement, are proportionate to the risk that is currently being addressed. And we should be transparent, fair and accountable, but important, consistent. And I think that's one of the messages the industry was keen was implemented as part of a national regulator, that wherever you are in the country, the response and the reaction from the regulator should be the same for the same type of problem with the same type of scope. But this then ends up in the co-regulation model that we operate in, which at times might cause some debate, but ultimately everyone has distinct but complementary responsibilities. Governments make the law. Governments in the states and territories have passed the rail safety national law. Industry, the rail transport operators, are responsible for safe railway operations, and the regulator administers the law. But the ultimate responsibility, the safety duties for safe operations, and perhaps for today thinking about what safe maintenance might look like, rest with the operators. The regulator is there to ensure and encourage the operators to be doing what the operators should be doing. The regulator, perhaps unlike the American model that Chris has already alluded to, does not approve, does not own things like maintenance standards. So standards then. Why bother with standards, and what are standards, and is it relevant to the rail safety national law? Now, we're all here to talk about maintenance standards, discuss them. There's a whole host of standards out there that we work to, and I'm sure we all recognise why we need them. Perhaps at times you might need to have a bit of a debate with colleagues about the value of some of the standards, but whether you think having them is a good idea or not is perhaps immaterial, because the law says you shall have standards. And in terms of a foundation perhaps for today's discussion, I think that's important to recognise. Before you get too worried, I'm not going to go through the whole of the law and regulations and repeat them all to you today, but I just thought I'd throw out a few key ones to put into context the discussions we'll hopefully be having. So a key regulation there is Regulation 19, and for those that don't know that off by heart, unfortunately I've got the words in front of me too. Regulation 19 is about general engineering and operational system safety requirements, and it's about people having a documented set of engineering standards and procedures and operational system safety standards and procedures for infrastructure, rolling stock, operational system and their interfaces. So there is a legal requirement to manage safety, and to do that, to have engineering standards for your infrastructure and rolling stock. So as a basis for today's discussions, you can always have that at the back of your mind. So that's specifying and understanding the nature of the asset that you've got. And the second half of that regulation moves on from having the standard to describe the what to having the standards and the process to describe how. So systems and procedures and standards for infrastructure and rolling stock that cover the asset life cycle from design through to decommissioning. So yes, it's important to have the maintenance standards, for instance, that will describe what you might look at and examine, but you also need the processes surrounding that to ensure that that standard gets implemented and delivered. It's just to think on two fronts how that is done. So effective standards. What are effective safety standards? Can we take the assumption that standards have been written, we've got all the documentation that we need, and that they comply with Regulation 19? So tick, 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 we're all good to go. Well, not necessarily. We have to ensure that our standards are effective and are implemented effectively to ensure safety. And the example I gave at a previous presentation, and apologies for those that might have heard this before, but it's an event that stuck in my mind. But a few years ago, in fact probably many years ago, I was working in Dublin with Irish Railways, and we were delivering a number of things, one of which was level crossing upgrades. So level crossings were being upgraded and all of that was ticking along okay. And then I got the phone call that I realised you all wait for too, which is a phone call from the equivalent of the Irish safety regulator, announcing that they would like to come out and have a look at what's been done. So, of course, with a great smile on my face on the other end of the phone, you say, yes, we'd welcome a visit at any time. Would you like to come out? So we arranged that inspection, and the regulator came out, and we had stopwatches and tape measures, and we measured boom lengths, boom heights, flashing rates, everything about this level crossing. And at the end of the inspection, the regulator said, well, this all looks okay. No, everything's in as it should be, but just one question. The road signs on the approach to your level crossing are black letters on a white background. I think the current standard is black letters on a yellow background. So it's the regulator asking the question, and of course, I'm sure like everyone else, when the regulator asks a question, you take it seriously. So you go, yes, well, it's a white background because it's been through a design process, it's been checked and approved, it's come out to site, we've procured it through our processes, it's been inspected on site. I'm sure it's okay, but if you think it's a yellow background, I'll take that seriously and we'll go and investigate it. And when I got back into the office, the first thing I did, it was actually quite easy. Being a signal engineer, it was the civil engineers that designed it, so it was someone else's problem. But phoned the civil engineer construction office and said, oh, Andy, how did the inspection go? And I said, swimmingly well. Just one question. Oh, black letters on a white background for the signs, or black letters on a yellow background? And there was a pause, and the comment came back, might be on to something there. I said, well, what do you mean? And he said, well, the standard is an Irish Department of Transport traffic manual, and it costs €300. So we've just got a black and white photocopy. So within the week, the correct signs were back out there. But the message there is, you can have the standard, but are you using it effectively? Are you aware of its limitations? And yes, we can tick off, we've got standards that comply with Regulation 19. Doesn't necessarily mean our railways are safe, particularly if you don't have a colour photocopy. So just think about how effective your standards can be. But in reality are some of the key features of effective safety standards, and that's across the asset life cycle. Ideally, risk-based development behind them, so we can understand, at least from the regulator's point of view, what safety risks might be controlled. There'll be other risks in there too. There should be a clear and accountable development governance to the standard. They should share good industry practice. They should be subject to continual improvement and review. And in so many parts of our professional lives, I think continual improvement should always be there. And again, I think that's one of the strengths of forums such as this, where we come together and we think about what's out there. How can we do what we're doing better, or can we learn from someone else? Someone escaping. Standards are a useful way of documenting safety so far as is reasonably practical type controls. And these controls should support the hierarchy of control mechanisms, and standards should also have clear decision-making accountabilities. At times, we need to intervene, we need to make decisions, and it should be clear as to who does that. So again, linking that back to the national law, I've got some references there. So section 47, as I'm sure you will all know too, reasonably practicable. So the law there talks about the availability and suitability of ways to eliminate or minimise risk. Well, what are the ways to do that? If you don't have standards, if you don't have maintenance standards, how would you know that? So actually having standards that document the ways of doing things, you're contributing to being compliant with managing risk in a reasonably practicable way. If you're a rail infrastructure manager, and if we're looking at track today, that's highly relevant for a rail infrastructure manager. A RIM has duties under the Act too, which is a whole host of things there over the asset life cycle. But the manager of the manager's rail infrastructure is designed, maintained, etc., is done or carried out in a way that ensures the safety of railway operations. How do you define the way? If you don't have standards and you don't have effective standards, how can you ensure that takes place? So again, the safety law there is underpinning what you're doing anyway. I wouldn't think much of this would be new or will create a change in direction. But I think it's important to be aware that the work you're doing in track standards, be they maintenance or design, is underpinning your approach to managing safety. In section 55 there, on due diligence, which is in the national law, I was just checking the Victorian version, and that's why I've got a little comment in there, but whether it's in the Victorian legislation or not, if you're an engineer anyway, I think you've got a professional responsibility to keep up to date in due diligence. But how do you acquire and keep up to date knowledge of rail safety matters? One way is to keep up to date and keep your standards up to date. If you have an organisation that has maintenance standards and you review them and improve them and communicate them, then you're ensuring your workforce and your organisation is being kept up to date with knowledge of rail safety matters, of knowledge of new ways and better ways of doing maintenance. So standards and the law are actually linked together, and I think that the law there gives a foundation to the discussions today. I don't think it will change your thinking or your direction, but I find it useful just to have that at the back of my mind. So maintenance standards. Our existing maintenance standards, I think, provide the basis for our current maintenance plans, and they'll support current reliability and performance. That's all good. Are there opportunities for improvement? And I have some questions here, and it may help later on, may not. But do the current maintenance standards optimise cost, risk and performance? Now, from the regulator's point of view, risk there is really safety risk, but I'll admit that the world is slightly bigger than the regulator's core interest. Cost, risk and performance, that comes back to the messages behind ISO 55000, the new, it's probably not new now, asset management standard. And if you're looking at maintenance, you've got to work out all of these and how you balance these things together. Certainly, from the regulator's point of view, interested in failure consequence and that risk side of it, particularly safety. But have you thought about the asset's environment? Are our maintenance instructions and approaches efficient for the maintainer? If we're spending a lot of time doing something that doesn't add value, could that time be better spent doing something more useful elsewhere? I think these are the sort of questions to be thinking about. And the challenge there really is about continual improvement. You'll all have seen the continual improvement cycle that's taken from the Asset Management Council. But it's important to understand what the failure consequences are, and if we don't understand our failure consequences, we're not effectively managing safety. And if we don't understand our failure consequences, how can we be innovative or effectively review the maintenance that we are doing? So I think that's part of the challenge we face. So how do we review effectiveness of our maintenance approaches? I'm sure there's lots of tools out there to help, and I thought I'd spend a few minutes talking about one tool that may not be appropriate for all situations, but it's just to show that there is a way of thinking about these things, and it's FMICA, failure modes and effects criticality analysis, which is a systematic way of addressing failure modes and their consequences. And if you're going to look at maintenance and understand what you're going to do and why you're measuring or looking at things, you should ideally, I think, understand why you're doing all of this. And FMICA can enable the build-up of effective maintenance tasks. So hopefully the slides will work here. It's maybe a bit small. I'll try and talk to them. But there, at the beginning, is really about understanding what assets you have, how they contribute to your business, and what they do. And unless you've got an understanding of that, in effect, the context that our physical assets are in, it's going to be a bit of a struggle to work out what you should be doing to them to keep them safe and reliable. But if you understand what functions an asset performs, you can then start to think how it might fail. So you can see failure modes in the top of the 3 box. Once you know what the failure modes are, you can understand what the effect of that failure is. And you can also then start to think about the probability of the failure occurring. So off to the right-hand side there, we can see our typical risk matrix, where if you have, say, a high consequence, high probability type risk or failure mode, you can identify mitigation that will reduce the risk. And in this instance, the mitigation that we might look at is maintenance. What maintenance are you going to do to reduce the risk of that failure mode? So when we're looking at new technologies, when we're looking at smarter ways of doing maintenance, how are we reducing the risk of failure? That's key, I think, to what we should be thinking about. And when you've started to identify these things, then you can find operator actions, maintainer actions. You may have to go back and redesign. But the operator and maintainer actions is our maintenance plans. And going through that systematic process then helps you identify the maintenance activity that you may wish to do. So a FMECA can help support safe assets because it helps you identify maintenance activities, helps you identify operational activities you should do, and helps you communicate the assumptions behind existing practices, because it gets you systematically thinking about things. And I think in so many things that we do in engineering, understanding the assumptions is as important as actually understanding what you're doing in the first place. And it provides a traceability between the maintenance programme and a safe and reliable railway. And again, that systematic way can also help you identify the gaps or deficiencies that may exist in your current maintenance activity or maintenance instructions or approach to maintenance. And I think that's one of the themes of today's workshop, is what are the gaps or deficiencies that we might have. Again, asset management, I was alluding to the how of doing maintenance. We have asset management plans, and asset management plans will cover things such as the management of risk, knowing or being comfortable that our asset hazards are identified and controlled. Some of the control there can be in the documentation, that we have instructions and processes to ensure that our maintenance is delivered. With our actual assets, that their safety performance measures are known and managed, that we've got training and instruction for our staff, and that everyone is competent in what they do. That is, in a quick summary, what might be part of an asset management plan. What maintenance standards and instructions will contribute to. That asset management plan is a requirement of a safety management system, which is a requirement under the Rail Safety National Law too. So again, there's this connection back that what you're doing today, what you're thinking about in terms of maintenance instructions and standards is fundamental to ensuring that you deliver a safe railway that is compliant with our national law. So track standards, typical content. As a signal engineer, I've got an in-depth knowledge of all of these. However, some of the things that we would be expecting that might be covered in track standards, and it's just to throw out some suggestions, as design attributes. You should be aware, I think, as you look at maintenance, of the fundamental nature of the design, track geometry, rail profiles, what the allowable speeds are, and some of these will also determine the risk profile that you're dealing with, that will inform you as to how you should approach maintenance, certain types of rolling stock configuration, or your desired stress-free temperature. Maintenance, and I know we might be concentrating on the technical aspects of the asset, but maintenance also includes the management of defects, corrective maintenance. It's not just always preventative maintenance, and knowing what our limits are in order that we can keep a railway safe in terms of track geometry, formation, drainage, etc. Again, I've mentioned too, and I'll come back to it again in a minute or two, the importance of planning maintenance activity. We can't just look at maintenance instructions, the kind of technical nature in isolation, but the planning of maintenance, which comes back to appropriate maintenance frequencies, and we might touch on that later today too, as I think often improvement in maintenance activity generally is linked to frequency. We don't often see improvement in maintenance that means you do a lot more often. That's not often the driver, but in terms of safety, we've got to ensure that maintenance frequencies are appropriate and what's done. And if we introduce new technology, have we got the competence correct for the maintainer to be able to apply the technology or understand what the technology is telling us? And as I've alluded to already, the management of defects, the information required to effectively manage defects, knowing who makes decisions and the accountability for these decisions. So, safe delivery. I didn't just want us to concentrate or just have that focus purely on the technical nature of it, but I do appreciate that's going to be important for today. But we do need to think about how it fits in overall. As a railway, we may be track engineers today, but there are a whole host of disciplines out there, and the railway is a complex system. A wide variety of disciplines, an even wider variety of technology, and assets at a whole stage throughout their life cycle. And we need to be managing the safety risk, as I've said. You need to be managing condition, you need to be managing interfaces, budgets, people. The whole thing is complicated. And how do we do that safely? And it comes back to our asset management and asset planning approach. So a safe approach, yes, I think it's appropriate that you focus here today on track standards and the engineering behind them, but we do need to think that all assets have to work together, whatever discipline an engineer is responsible for them. We have to be very aware of these interfaces, and as I've just said, we've got to think of the railway acting as a system as a whole. And a safe approach includes understanding risk, being aware of what the safety requirements are. That doesn't, I've got legislative requirements up there too, but what are the safety requirements on your asset? What performance does your asset that you're looking at maintaining, you're looking at maintaining a different way, what are the safety requirements? What's the rest of the railway expect your asset to deliver? And stakeholder requirements, which might come back to some more of the business drivers, as I was explaining earlier, that cost, risk, performance juggling act. So the asset life cycle is worth thinking of too, because when we're looking at maintenance, and asset life cycle, there's lots of ways of drawing that. Again, I think this one's taken from the Asset Management Council. But you plan, you design your asset, you acquire it, you build it, and then you operate and maintain it. And the design, the planning, the acquiring, the building might take 3, 4, 5 years, however long. It depends generally on the scale and nature of a project. But the operate and maintain, I think particularly for civil assets, is decades. An awful lot of effort goes into delivering a project to time and to budget. How often do projects adequately think of the poor sod, for want of a better phrase, who's going to look after this for the next 20, 30, 40, probably a lot more with track type assets, because the real challenge there is managing their activity and ensuring that what they're doing is safe. But assets need to be managed throughout that life cycle, and good maintenance standards, good maintenance practice begins at the design. I think perhaps with track assets there's not a huge revolutionary change that there can be with with technology assets, perhaps in the signalling field, but there is still change in track and civil engineering assets. And if we're introducing a new, better component or way of doing things, are we thinking about the maintainer? I remember too, when I was in the UK, we were looking, and this would be 15, 20 years ago, we were looking at a new switch mechanism, which I think might have come over to Australia, or was thinking about it. But to protect the innocent, I won't mention their name. But it had come up with a new switch mechanism for moving points across. Fantastic. They just looked at the problem from a completely different way, and we'd moved then away from an electric motor with maybe a lock in the stretcher bar or clamp locks, the things we might be more aware of. And they designed this thing, and it was robust, solid, but maintenance free. So the designer had designed it because it was on the basis it was maintenance free. And you think, well, fine, it's maintenance free, so you say, but the railways still like to do maybe a facing point lock test once a month, once every 2 months. That needs a bit of maintenance. You might say it's maintenance free, the thing will fail. Whether it's the fault of your apparatus or not, it will fail. But the initial design of this machine, it took, if I remember correctly, 25 minutes to get the covers off. And I'd say, well, why is it taking this long? Why have you got so many grub screws and different sized Allen keys just to get the covers off? And the response was, well, it's maintenance free. No one needs to go in and have a look at it. Now, that was corrected, I think, in subsequent versions. But when we're designing, when we're involved at the beginning, that's when we can have the biggest impact, I think, on operations and maintenance issues. So, multiple assets, we've got multiple stages. How we deal with all of that means we've got to plan for safety. Another example I thought I would share with you, this was a story where a coal train was leaving a yard empty. A handbrake had been left applied to one wheel, and the operator failed to spot the defect. These things happen, such as life at times. So the train wheel slipped along the track as the train progressed empty to the coal yard. And when the wagon was filled with coal, the wheel locked on the return journey. So the locked train wheel caused the laden wagon to derail at a junction. The resulting derailment damaged the rail system, the system as a whole. So the wagons were damaged, track was damaged, signalling was damaged. Operational disruption was somewhat scary. Ships were delayed at port. The estimated consequence of that one failure was about $10 million. That was based, that's a true story, but the scenario happened twice at the same location within 1 month. And it's thinking about what are we doing in terms of maintenance? How are we responding to these items? So there was a new piece of kit was designed to detect should a wheel be locked. But one of the messages here, I think, is when you're looking at your assets, a failure in your asset can have consequences in other people's domains within the railway system. A failure on a wagon created problems for the rolling stock engineer, created significant problems for the track engineer, created problems for the signal engineer, and did not make the operations manager a happy man twice in 1 month, assuming we are ever truly happy. But our approach to maintenance, and again, when you're thinking about maintenance today, think about how reliable and safe track assets contribute to the rest of the railway, and not just within the confines of the track engineer. So nearing the end, we also need to be aware of how everything fits together, how you manage your asset. Know the interfaces between assets, between asset groups. Understand that maintenance and your standards should be supporting your assets being fit for purpose. We've got to be thinking about how we actually manage the asset. We've got to know what we're doing with our maintenance standards and instructions, but how does it all come together? Because by doing that, we can manage engineering change safely. So, know your safety requirements, know how your requirements are managed throughout the asset life cycle, know how you manage your asset risks, ensure you've got the information that you need, and how you interface with other parts of the railway. So that really brings me to the end of what I was looking to talk about. We've had a quick skip through the ONRSR, who we covered, the changes coming up in New South Wales and Queensland about to join us, what the regulator's here to do. But I hope I've given you a foundation for the rest of the day to have at the back of your mind that what you're doing is important, it's critical for compliance with rail safety, and ultimately that's why we're all here. And some of the things to be thinking about in terms of maintenance standards, to ensure that maintenance standards and how we do maintenance is effective and safe. Thank you.
Thanks, Andy. So we're running on time on
Yep.
schedule.
Any questions?
So we have time for questions. Now, I don't know, were you having a microphone or we just...
I think people have to talk a bit loud, if that's okay. Yeah,
Okay.
it's a smaller room.
Yeah, thanks, Barry.
Can I go with the first question, if you don't mind? I think, Andy, thank you very much for covering the wide range of things and showing us how the law works with the safety. My question is, I think you covered a lot on the risk-based maintenance and identify when the risks are high. But in my experience, I think we take that to saying that we actually catch the failure and then try to fix the problem. And that risk base is actually not to, I think probably yesterday Gary covered, I think you don't want to get into an airplane and say it fails and then we have to fix it. I think we want to actually identify before it actually fails. And that is not really covered very well in the standards, in the sense we don't really use standards for that particular purpose. We're only using the standards to catch the failures and then trying to fix the problems. That's my understanding. Is that?
Your understanding, I think, on one level is correct. I mean, there's two, there's different types of maintenance, and I think what you're talking about there is, first of all, corrective maintenance. A failure occurs, how do we ensure that corrective maintenance deals with that safely? And that's about defect management, and standards need to be able to identify what is a defect, how we respond to a defect. Do we need to shut the railway? Do we need to put conditions on? How quickly do we repair? Yes, that often is how we respond to maintenance type failures or a failure. But we get smart when we work to predict or identify a degrading asset. And that then gets us, I think, into preventative maintenance or condition-based maintenance, because that point of failure, when something fails, it's a hazard. and a hazard is a risk, and we manage the risk. If we can prevent the hazard occurring in the first place, that is a risk-based approach to maintenance, because it prevents the failure happening in the first place. Should a failure happen, yes, we've got to manage the subsequent risk, and we should be good at that. We can always go back and review. But the two things are different. One's managing the resulting risk, corrective defect management. The other is preventing the risk happening in the first place, which is a risk-based approach to preventative maintenance, condition-based maintenance. Does that sort of answer your question?
Yeah, I understand
Yes.
what you're saying. But I think, do we have any standards covering the preventative maintenance requirements, and how do we actually get that into the psyche of railways to actually think of preventative maintenance? Is it now currently covered in our standards?
In whether it's covered in standards or not, I can't comment, because each operator will have their own standards. But in terms of the rail safety law, if we want to go back to there, if we're in the game of managing risk, so far as is reasonably practicable, can we eliminate the risk? And if we can't eliminate the risk, what can we do to mitigate the risk? If we have the technology and the smarts to prevent the risk happening, that's eliminating the risk. So I would suggest that the law would be driving us towards a space where we get better and better at predicting failures to prevent them happening in the first place. So I think the failure prediction, condition-based maintenance, yes, it's something that I'm sure everyone here will be interested in and will drive towards, but I would also say that the safety law would thoroughly support that direction at its base.
Thank you.
Yeah, thanks.
John Paff, Transport for New South Wales Asset Standards Authority. In the true spirit of a workshop, I've got more of a comment than a question. In your own words, and I can't do the accent, but you said the world is bigger than the regulator's requirements. You at one point there you said
Yes.
the world is bigger than just the regulator's requirements for safety. I think that's a really important thing for people to remember. Sometimes you get too focused on safety and forget that bigger picture. I think we should go about our business with safety as a given. It goes without saying that things will be safe. That safety is not negotiable, I think is a good way to go about it. And raise your sights above that safety and get into asset management to manage, instead of managing the safety of, instead of getting tied up with managing the safety of the asset, if you think more about managing the value of the asset, safety will follow. Of course you don't drop, safety is a given, it's not negotiable. But if you raise your sights above the defect identification and get into the condition monitoring, that's where people should be. So your initial point was the world is bigger than the regulator's requirements. The regulator doesn't have requirements on whole of life costs, on maintaining the value of an asset. The world is bigger than just that.
Yes. And in the spirit of a workshop, I could reply to your comment with a comment. So I would agree with that, absolutely. And the key, I think, or the takeaway from what I've just been talking about is really just to set a foundation of safety. The safety law is there as our foundation. It's relevant to what we're doing today. But the challenge, I think, for today in the discussions, and as we go about our business after today, is how we move above that foundation into what you're saying. Yes, safety is a given. It's the foundation. Yeah.
Just a quick one. Alex Pugh from Police Rail. Just a question on standards. It's just your thoughts on whether the standards should set the limit, as in the minimum maintenance limit. And then you talked about the project he builds in is brand new, and that should be to a prescribed standard. At what point do you think the standard should just define the maintenance limit, or whether it shouldn't? You
That's a good question. I'll need to take my regulator's hat off because the regulator can't have an opinion on that. But intuitively, I think you have to go back and think, what am I going to use these standards for? If you're going to have an absolute limit and you've got your system set up to deal with breaching that absolute limit, you're probably getting back to the point that Avi was making. You've got the defect, we're now managing the defect. Maybe I'll put my regulator's hat back on there. But if we're in the game where we don't want to get to the defect in the first place, then perhaps you need some limits or some flags or some measures to say, this asset condition is heading to a place that we're not happy with. Intervening now will prevent the defect occurring. But again, it's not a one-size-fits-all. I think it depends on the nature of the asset and where it is and what's being operated on. I'm a believer in maintenance. You can't say everything must have every single limit worked on and dealt with. A bit of track in the main line may appropriately have certain intervention limits. The same bit of track in a siding somewhere, you may not really bother with. I think that's being smart, and it's maybe get back to John's point. That's about how you manage the asset and your asset management plans and your asset management approach. But a one-size-fits-all is, I don't think, will end up with an effective solution for you.
I might ask you a question, Andy.
Please.
You've satisfied the floor.
Is that a comment or a question?
So, we've got a track manager who's gone through the risks and looked at the risks of derailment, for example, and they're working through a range of controls which are mostly known, and in amongst them, possibly a few new technology ideas, such as, let's say, monitoring rail stress real time. What would you say to them about how they should actually balance and weigh the options of new technology versus, oh well, no, we're just going to do creep on you. It's what we've done for 100 years, and we'll keep doing it. So it's just an example of new technology.
New technology exists, and the world has always moved forward with new technology. If the railway hadn't moved forward with new technology, it would still have a man with a red flag walking in front of a train. So we have to respond to new technology. And as I said at the beginning, the regulator supports new technology. The regulator supports innovation, provided it is implemented safely. Just throwing and implementing new technology because it's new technology, probably not a good way. In that scenario, I'd be saying to the track manager, terrific. You've met some of the requirements of the law because you're going out trying to understand ways of doing what you're doing, trying to keep up to date with new ways of doing what you're doing. But before you implement it, do you understand the risks associated with the change, and can you demonstrate that what you're doing does provide a safety improvement?
Yep. And if he further said, well, I'm actually quite satisfied with the way I'm doing it. I'm not going to look at new technology. What would you say about that? So he's aware, and you're aware that there is available technology, and he's not really doing much to look at it, but he knows what he's doing, and he's just going to continue to do it the way he's done it, which is measuring creep over time.
Oh, that's good, Chris. That's good. Personally, I would feel a bit frustrated, but with the regulators hat back on, ultimately, under the law, the safety duty rests with the rail transport operator. And if the rail transport operator, the track manager, can demonstrate that what he's doing is managing safety so far as is reasonably practicable, there's not much more the regulator can do. If the new technology is making his life more effective and efficient and he's choosing not to do that, that's his call. If not implementing new technology means that he's no longer managing his track asset safe so far as is practicable, then there would probably be a different discussion. But that really would need to be a significant change in approach where the cost of the new technology gives a blatantly clear safety benefit, and that new technology is available and he's deliberately choosing not to use it. It'd need to be kind of in that black and white area for the regulator to be involved. But ultimately, the rail transport operators hold the duty, and its industry day to day has the challenges of delivering safe railways. And the regulator can dip in now and again and see what's happening. But I think the really difficult job is in industry delivering safely day to day. So ultimately, if there's a reasonable call by a reasonable track manager, that's his decision, as long as he's still managing safety so far.
We could have a whole discussion about so far.
We can. Thanks, Chris.
Thanks very much, Andy. So can we share our appreciation? So we're bang on time. So we have 15 minutes now for morning tea. Back here for the next speaker at 10:30. Thank you.
Just be back on time because we want to really start the session on time. So please come back on time. And when you're going out, you can actually keep your token as well. I think so that you know which one you're going to be in. Connie, do we have the token? Okay.
How are you? Nice to meet you. Now, I'm not on until...
So it's Gary next, and then no break. It's straight into you.
Okay, what I wanted to do, let's go to the desktop. My presentation, I thought was on the desktop.
This gentleman's going to help us.
Hey, is my presentation?
Yeah, it's already integrated.
It's already in the slideshow.
Oh, I was going to add a slide. That was all.
If you go down,
Here we are. Yep, that's right.
keep going down. Down. Keep going.
Oh, there's quite a few, isn't there? Someone's got a lot.
Scary.
Of course, he's got a lot of shows. Okay, so catching up, I think.
Catching up. Yeah.
Not responding.
Stupid as fuck.
Okay, now we're right.
Just keep going. On this side.
On the side?
Yeah, on this side.
150.
There we go. This
Excellent, thanks. I just want to add one in there.
No, that's all. Just put this slide.
Can I turn off these screens so I can just do it here?
The thing is, these screens are linked to that, so you have to look up there.
Okay.
So,
Beautiful.
So
you have to do it up front if you don't want to there.
No problem.
I had trouble because it was echoing.
yeah.
You've just got to make sure the microphone's not.
See, we're getting feedback from these speakers.
Maybe if you step back towards the wall.
Yeah, maybe back there.
How's that? Try that.
I think you're still getting feedback.
No.
No feedback?
No, no feedback.
That's-
If you
that's
stand
good
there,
back
there's
here.
no feedback. Isn't
Okay.
it? No feedback from there.
It's much better.
Yeah,
It's still
Yeah.
yeah. It's poor acoustics in this room. They
Yeah,
didn't
can't do anything about
see,
it.
that's crazy.
But there is a microphone here. Try this one, but the only thing is you're going to be blocked off by that.
Yeah,
what-
and, you know, when the speaker stands behind here, you can't see the speaker.
How's that? Is that better? Yeah, that one down. Oh, it's a design that somebody has done it without even realizing. How is that? Yeah, so you might be able to.
Projectors in the way.
yeah, no, that's good. Now, if I want to put that slide, so that slide's now done. Now it's currently there.
I think you've got to drag it down to where.
No, I'll leave it where it is. That's no problem. So now we just need to go back to wherever we.
Yeah, I'll sort that out. All
Okay.
Good. All good.
Thanks
Yeah,
very
no worries.
So
This is horrible.
That's the case, yeah.
This is horrible.
Yeah, I don't think you need a microphone, Gary.
Well, maybe not. I speak up. Yeah, I'll try without it. It's a small group.
It's a current term du jour, isn't it? Apparently.
Oh, great. Hey, thank you. Perfect. See, he should be in charge of acoustics.
Yeah, exactly.
Proud member of the group.
Let's grab a seat, please.
All right, can you take your seats, please? While we're waiting, can I just check to see if Rob Sayer or Yock Wynn from Sydney Trains, Rob Sayer from Melbourne Metro, are in the room? Yock Wynn? Okay. Rob Sayer? Okay, so the other thing is, if you don't all have a number, please see Connie, who's at the end of the room, at the beginning of the next break. You'll need a number to get a group for doing the activity after lunch. So the cave and the
Drum.
drums. Yep. Right. So the next question is, how many people weren't here last night?
Wow.
Yeah, so a few. All right. So many of you have already been introduced to and heard Gary Wolf speak, but for those who you haven't, Gary's a railway consultant from the US, 46 years experience in the rail industry, 17 years at Southern Norfolk Railway, 26 years as a consultant and owner of Rail Sciences, last 3 years in private practice. This number impressed me. He's investigated over 4,000 derailments worldwide and trained over 5,000 railway professionals. So you'll see in the thing, he's got a very extensive biography, very well qualified and credentialed. So Gary has a Bachelor of Science in Electrical Engineering from Ohio University and a Master's of Science from Georgia Tech in Industrial Management. So he's an electrical engineer like me.
Correct. We call them wire twisters.
As distinct from ballast spreaders and timber healers.
Exactly.
Okay, thank you.
Thank you, Mr. McEwen. Okay, we're having some acoustic feedback. Can you all hear me in the back? If I speak a little loud, okay. We won't deal with the microphone then. The topic I'm going to introduce kind of flows off of what our previous speaker was talking about on standards and things. And the germ of this speech I'm about to give has come from my experience, particularly in derailment work and also in my work in wheel-rail interface and optimization and wheel-rail interface. It was very typical for me, and you saw the numbers. I've been in derailments since 1975, and so nearly 42 years now I do derailments. If you wonder how somebody gets to 4,000, I was doing 15 to 20 a month derailments. Now, not big explosion derailments always, but even one-wheel derailments at our railroad were important enough to get the root cause. And I would perform simulation analysis, sometimes field studies, whatever it took. But I've accumulated a lot of experience. And here's a typical phone call that I would get, at least on a monthly basis. Phone would ring, hello, Gary, we've got a problem. I go, what's that? We've got 20 cars derailed, 20 wagons. We've checked the track, meets the standards. We've inspected the wagons, they meet the standards. We reviewed the event recorder, the crew performance met the standards. We've got 20 cars on the ground and hazmat experience, etc. That was a very common call. So you wonder why I am an advocate of maybe revisiting our standards is because of this frustration that has led from my experience of those kinds of phone calls. The standards have taken us for, what, almost 200 years now of railroad history, close to it. They've taken us a long way. But now with technology improvements, I think the time is ready for us to step back and assess what we can do to take these standards to the next level. We have tremendously reduced derailments in North America, Canada, U.S., Mexico, by nearly 50% in the last 10 or 12 years. That's a tremendous achievement. I'm not happy, though. I will not sleep well until that number is zero. Okay, there's no reason to ever have a derailment, especially with the technology at our fingertips today. If we use that technology properly, we can bring those numbers down. We've kind of plateaued. We get a little complacent. We go, oh, we've done great. We got it down 50%. Well, guess what? We're still having derailments, okay? And some of them you see on the news from time to time. It's not good for our industry. So, this is what I want to talk about, is maybe a new way of looking at assessing geometry in particular in regards to derailments. So what I'm going to cover today, first I'm going to start off with a few quick case studies. I'm going to go quickly on them, just give you a little flavor of a couple cases I pulled out for this presentation where we had track geometry issues that met all the standards, and yet we had significant derailments occur operating over that piece of track, even though it met all the regulatory standards. Next, I'm going to discuss a new approach using modern detection and monitoring technology, which was our theme last night, and will be a continuing theme today. Graham is up next, talking about some work Monash has done. I'm going to talk in the afternoon about better and more improved monitoring and detection work on the track infrastructure side. And then I'm going to show how we can throw this into, or put it into, a risk assessment model using all this data that we now have at our fingertips to come up with a more realistic approach and move from what I call condition detection, that is a measurement of a cross level at a discrete point, a measurement of a gauge, a measurement of a surface, versus a performance-based system of how vehicles will perform over that track given these parameters that we can now measure with a high degree of regularity. So that's the basic premise here of what we're going to discuss. The first derailment I want to show you was a loaded box wagon operating over a highly elevated curve. I won't get into all the reasons why the curve was highly elevated, but it had something to do with past experience with passenger trains on that corridor needing higher elevation for their speeds versus freight speeds, which is a common problem in many areas. The curve elevation reached about 7 inches or 178 millimeters. You'll see in a moment with the graph. And the curve also moderated at the same location. So we had an increase of elevation, a lessening of curvature. The train was operating at 10 miles per hour, 15 clicks roughly, considerably under balance speed or design speed for the curve. The higher elevation was due to pumping, mud obviously, from the low rail side. So when the low rail goes down, the high rail goes up in essence in relative terms, and the elevation that increases. That's what was occurring. And also, the curve had corded in during the winter. When the rail contracted and the ballast was weak there, it pulled that curve inward. That's why the curvature changed as well. As I said, none of the track conditions constituted a regulatory defect. And of interest, the first derailed car in this train, I forget, 50, 60 cars, one car came off at this spot, had a slightly off-centered load. Now, we can sit back and say, well, there's the cause. The load was off-center, an inch or two from center of gravity. The problem is, that's a reality that we should recognize in our world. When we set a standard, we should accommodate an off-centered load, okay? Not to a great degree, but say minor offsets ought to be considered in how we look at standards. And not assume every wagon coming down the railroad is perfect, okay? I think that's one of the fallacies when we look at standards. So here's our elevation. The red line is curve elevation. As you came into the entry spiral of the curve, it ramped up to about a nominal 5 inches of elevation. And at this one spot at the entry of the body of the curve, it went up to 7 inches. Unfortunately, although that looks ugly, it was not a regulatory defect by the book. It was close, but not a defect. Okay? So we could turn our heads and say, no, it's not a track issue. Let's blame it on the off-center load. So we simulated the performance of that load over that piece of track, and what we found as we entered the curve, the L over V ratios. Is everybody in the room familiar with L over V ratio? I'm not speaking over anyone's head here. Okay, that'll be very cool. Increased, and curiously enough, what happened here, as it hit that spot, it started a resonant kind of roll motion. And when it got to the eventual point of derailment, which was not the spot with maximum elevation, but a couple, maybe 50 or 200 feet down the track, is where the L over V peaked at over 1.0. Now, typically we say when a single wheel L over V hits around 0.75 to 0.8, the common Nadal ratio, that's when wheel climb becomes evident. So we were able to predict pretty accurately why the wheel climbed there. It was this response to that severe perturbation, yet not condemnable, etc. Now the red line shows what would have happened if the car had a nominally centered load or was perfectly balanced. And you see the risk is quite low. But given that the car had a few inch offset on the load, we did predict a derailment here. Now, we also looked at what would have occurred if that curve had proper 1 inch or about 25 millimeters of elevation, which would have been the proper elevation for the speed. And we see that the L over V ratios, both with the existing car off-centered or with the car perfectly centered, are quite benign, certainly under 0.5, well below the threshold for wheel climb. So, the severe cross level and elevation increase introduced a harmonic roll action leading to wheel climb further down the track at a location of marginal twist. If the car did not have an unbalanced load, the derailment would not have occurred. And if the curve had been elevated to a nominal 1 inch, the derailment would never have occurred. 1 inch elevation would be normal for this degree of curve and a 10 mile per hour speed. So here we have a condition where we met the standards, but we put ourselves at an unacceptable level of risk, I think. So combinations of conditions, none of which are condemnable, can lead to derailment. Now this is not a derailment, but we did some work for a particular rail operation, looking at rail wear and things of that nature, and in looking at some data, we came across the fact that at one spot we had the low rail of a curve experiencing a sudden increase in wear, and the high rail gauge face also experiencing a sudden increase of wear. This was in a curve, and all of a sudden at one location we had these two blips, okay, increased wear rate. So we utilized and looked at the track geometry to see what's going on. Now this is, to set the stage here, this is I think this is the low rail, this is the high rail, and these are two successive measurements about a year to 2 years apart. And you see the rate of change is quite significant right in certain areas here. These two spots in particular, we saw significant rates of change compared to the rest of the curve. So we knew something was going on right here, this is low rail and high rail, to increase both gauge face wear and head loss on the low rail. You know, just a zone of about 100 feet, 30 or 40 meters, something like that. When we looked at geometry and overlaid the geometry, we found a sudden change in curvature right at that very point where that was occurring. To show you a close-up of the rail wear conditions, this was what most of the curve looked like between measurements that were roughly 2.5 years apart here. A little bit of gauge face and top wear, a little bit of head loss over here. But at the spot of concern, look at the change, the large step change in wear rate, both on head loss and on gauge face wear as well. So we ran some simulations with the vehicle dynamics model, and here's what we saw. That with the actual track geometry, with the curve variation right there, We saw a large increase in lateral forces on the low rail, as well as the high rail over red, which is your, which I would say would be normal geometry, smoothed out without that abrupt curvature change. And by the way, that was not a regulatory defect either. Okay, met all the standards, but it caused a huge degradation of our asset here. Looking at the vertical forces, the same kind of thing at that spot. And if we plot the kind of the energy, this was back when we didn't have the more sophisticated wear predictions, but we used total energy expended over the friction forces and creep, etc. And we found that with that one misalignment in the curve, a minor misalignment, we had nearly a 50-some% increase in lateral, low rail tread wear, and high rail flange wear, 100% increase in that. And that shows you again why small changes in geometry can have a big effect on our infrastructure. Here's another case where we were going along looking at rail wear conditions, and all of a sudden we noticed in a certain area over several hundred meters a rapid increase in especially the low rail wear, head loss occurring over 2 successive intervals of measurement. And also in concert we had a number of areas of rolling contact fatigue on the low side of the curve. So we want to take a look, why did that area stand out in its wear rate? What was unique about it? And what we found was it was on a downslope, loaded trains coming this way, okay? And they were often slowing in this region for a meet at this crossing loop right here. And so trains were slowing down coming into this meet location, and the curves back up here, we're experiencing trains operating significantly below the planned speed limit, okay? And again, when we did the computer modeling and simulation of vehicle dynamics, we found that the vertical wheel loads at the typical speeds that trains were approaching that area of around 11 to 10 mile per hour, 15 to 17 kilometer per hour, a very significant increase in the low rail force versus the high rail vertical forces. You don't like to see that imbalance. As we moved our speed up to 19, 25, and 30, the desired speed for that curve, we see the forces are in balance. So once again, it's pretty simple to explain here why we had the high wear rates, what was going on at that location. Also, it affected the lateral forces as well. When you operate significantly under balance speed, especially on the low side of the curve, your lateral tread creepage forces is increased with increased normal force, and that explains some of the tread wear issues as well. So we have 2 case studies here. One shows the direct influence of a sudden, non-condemnable change in geometry that causes higher than normal wheel set forces and wear. And the other one shows how the influence of train operating parameters can also influence the condition of our infrastructure if we're not taking that into account. So these studies show why we can't ignore even subtle changes in geometry, or we risk the development of adverse rail degradation. The problem is we're not detecting these changes. Geometry car goes through, clean bill of health, no problem, but boom, we see the results of some of these changes that we're not picking up. This one is, we had 3 high-speed box wagon derailments. These were 60-foot wagons, roughly 20-meter wagons with swing motion truck. They were derailing at a high speed, 80 miles per hour would be what, 125 or something kilometers per hour, high speed derailments. And the 3 of them occurred over about a 4-month period with similar track conditions. These were vertical perturbations near level crossings. However, again, importantly, they were below the FRA limits. Geometry cars didn't flag them in all 3 instances, yet we had significant derailments at all 3 places. Just to show you the plot of the laser plot using a laser survey instrument of the 2 rails, we saw significant vertical surface perturbations, 3 in a row, leading up to a level crossing here, and the point of derailment was just over that level crossing. So when we look at the top of rail profiles plotted left and right, red and green, we see this this change in vertical surface commensurate with some mud spots and things. We see 3 in a row, and then we have the point of derailment right in this area here. And also right before there, the 2 rails were roughly a 1-inch cross-level change as well. So we had a combination of twist right on top of 3 successive vertical perturbations. Again, all 3 sites, track geometry car did not flag any condition of concern. When we ran the vehicle simulations, we see the typical response in bounce at a high speed. We saw two large wheel unloading events down to 0 wheel load here, practically 0. And then right here, we hit 0 wheel load. The car went airborne, essentially, where the wheel lifted. And in concert with that geometry change, we got a huge spike right there in the derailment. So, again, small track surface defects, borderline, regulatory defects, multiple perturbations in a row. A single perturbation would not cause the derailment. You need that combination. And while the static measurements may meet the standards, the dynamics do not. And again, lack of corrective surfacing or grinding leads to these worsening conditions. Here was a passenger train derailment, pretty kind of famous one in the U.S. that made the newspapers about 10 years ago. And this is a view. I'm laying down at the level of the track trying to shoot these vertical perturbations. But we had 3 in a row. Train was operating again at about 80 miles per hour, 125 to so kilometers per hour. Had 3 of these perturbations, and you see they look kind of ugly here, but they were not regulatory condemnable. So we had these dips, about a 1 3/4 inch maximum was the worst dip, but the regulatory maximum allowable was 2 inches. So again, it wasn't flagged for either vertical or cross level. We were close, but not in the condemnable range. And here again is looking both east and west of the site, and you can see the vertical top looks pretty ugly, but it met the standards. So here's the 2 profiles plotted again, and we see left and right, purple and blue. We see 1, 2, 3 successive in a row, and then here's the point of derailment, the heavy red line, and also we have a twist condition right before that. Again, none of which were flagged. That's the cross level there. That's as measured. This is the input to our simulation model, showing how we modeled these dips, left and right rail with the attendant cross level change. And we ran speed sensitivity. I won't bore you with the details, but again, right at the point of derailment, we predicted a significant unloading event right in here, about 40 feet before the point of derailment. Now, when you're moving 80 miles an hour, that's a third of a second or so. We had complete wheel unloading at 79, 70, and 60 miles an hour. When we dropped the speed to 50, it got a little better, but it was, again, this combination of resonance that builds with successive dips that the geometry car was totally missing. Won't waste too much time here. We looked at things like, what if the dips, we made them 80% of the amplitude or 50% of the amplitude, or we took a couple dips out, or we made the dips longer so they weren't quite as severe like this. We kind of said, what if you came in and came out like that? We looked at a number of things, and yeah, we could see how geometry improvements would modify the situation there. So again, not to beat a dead horse, but we had these 4 dips right in a row. A singular dip would not have caused this derailment. The cross-level twist on top of it. So here we had combinations, again, of non-condemnable measurements in combination with speed initiated a major derailment of a passenger train and numerous injuries. Not a pleasant situation by any means. This last case was a very unique one. I thought it was quite interesting. We had a gauge widening derailment in this curve. Coming out of this curve here. Train was coming towards you. This is the high rail looking towards the direction the train was coming. And the derailment started to initiate right in this area here. You can see a severe alignment change right there because they had installed a 20-foot plug rail, which is 6, 7, 8 meters, whatever. We had an ultrasonic defect there. They went out and thermite welded in a plug rail, and you can see the alignment that resulted was not very good. Met all the standards, no defect, but look at it. So, right where we had this plug rail, right in here, coming out of this curve, we started to see dynamic gauge widening. And right up from about here into the point of derailment, the gauge started dynamically moving. This was on wooden sleepers, and you could see the plate movement that was occurring. I'll show you some pictures. The nominal alignment using a 10-meter cord roughly was 3/4 of an inch. Converted to a 20-meter cord, it was about a nominal 3-degree curve, which is, what would that be, 600 some meters maybe? About a moderate curve. So we had good track data, but we see this alignment change showed up on the cord measurements quite clearly here, right before the point of derailment and in the area where the gauge started to widen out. And so people thought, well, what the heck does an alignment defect have with gauge widening? It was very moderate. It wasn't significant by any standard that we had. So why did we get gauge widening at this site? Also, to make the matters a little worse, we also had a change in elevation right here. Although the curvature held strong, the elevation ran off. Again, we throw in this combination issue of twist on top of other things happening, in this case alignment, and we see the deadly combination of the two. So this is the gauge measurements where we had the severely wide gauge right preceding the point of derailment. Now here's another interesting thing. Wheel rail contact geometry. How many of you at derailments go out with a mini prof or another instrument and take wear profiles? I'm curious. Anybody? Just one, two? Okay, couple. Mr. McHugh, do you guys use rail profile instruments to measure accurately?
We don't have them, but we generally get that.
Yeah, you can get it, okay. A lot of people overlook the importance of wheel rail contact geometry. And to be honest with you, 30, 40 years ago when I started this stuff, we didn't really look at it much because wheel loads were lighter, conditions were better. But now as we've increased axle loads, upwards of 38, 40 tons now in the U.S. and North America, wheel rail contact becomes extremely critical, especially in curves to promote good steering. And what we found here, just to summarize it, we don't have time to explain why, but we had a very serious two-point contact because on the wagon that derailed, we have all new wheels operating on a curve-worn high rail, creating a two-point contact condition, which leads to essentially zero steering moment from that wheel set. Okay? So, when you think about why the gauge started widening there, it wasn't this one wheel that did it. This has been a successive boom, boom, boom over the prior 6 weeks. Many other wheels came through there with similar contact geometry that probably did not steer well, which even magnified the lateral loads in addition to the alignment defect on top of it. So here was the track here coming in. If you can see in the back, you start to see some plate movement here. As we got close to the point of derailment, this is the high rail. This is the low rail. The wheels dropped in somewhere over here. Again, looking back at this alignment, you can see the quick step change right in this area of the plug rail. And this is where the dynamic gauge widening, where the plates started pushing on this side here. Look, that is the low rail. Notice a very smooth geometry on the low side of the curve, which you would expect. So no problem there, to just to contrast it with the high rail. Now, if we look down on the plates, right where this started, here's the plug weld, thermite weld right here. Notice we started seeing plate movement, dynamic plate operation here. As we got further along, it got worse. When we got up here, we were seeing upwards of the worst was about 2 inches of dynamic movement on that sleeper. Now this curve had been measured by a geometry car about 4 or 5 months earlier. The gauge was perfect. No problem at all. They put the plug rail in about 6 weeks before this derailment, and we believe this was the degradation that occurred over 6 weeks in gauge because of a minor, non-condemnable alignment kink. We also were breaking spikes in the curve, dog spikes, cut spikes, whatever you call them here in Australia. And I'm holding a bunch of them. We had buckets fulls of them in that curve where those plates were moving, putting those spikes in bending, which caused a fatigue crack down on the shank. showing you some of them there. These were the wheel profiles on that car that derailed, showing essentially all new wheels, which is a normal condition, actually desirable. No defects were on the wagon. We did a very good teardown on that wagon. Looked at all the bogie pieces, took them all apart, just couldn't find anything mechanical wrong with the wagon other than it had brand new wheels. So we did some simulation modeling, and we particularly looked at the contributions of curve alignment and two-point contact, and to a lesser extent curve elevation on lateral forces and L over V's. I'll show you some pictures here. These were the three contact geometries we simulated. Conformal, a moderate two-point, which is essentially what the on-site measurements gave us, and then we looked at a more extreme two-point contact just for comparison. And we ran the simulations, and sure enough, what we saw is right at the point of derailment, we saw a very large increase in peak lateral truck side L over V's here, with the two-point contact versus the single-point contact, a pretty good hit. A 0.4 truck side is quite high, but the change was not huge, but it was a change, maybe 10%, depending on wheel contact. And I'll get to this. We also looked at smoothing the curve out. Here was the alignment kinks. We also looked at a more smooth curve. We compared the two, and we saw, again, a pretty significant change in alignment improvement from a 0.4 truck side predicted right at the point of derailment down to 0.27 or 0.28, 0.29 I guess it is. Again, that's a pretty significant improvement. So we see these subtle changes in geometry had a large influence, and I won't bore you with all these. Only to say that the smooth alignment is what was recommended to avoid these lateral perturbations, and we also mentioned to the client rail grinding to remove that significant two-point contact for newer wheel profiles. They had not ground that rail for some time, and again, back to wheel-rail interaction and the importance of it in generating lateral loads. So, I know I went quickly through those, but I wanted to give you a flavor of a lead-in to where I'm going to next take you as to what I think is a better system. But what we've learned from these accidents is that significant, yet not condemnable, variations in track and rail geometry first can lead to degradation of the track geometry and rail life, i.e. increased rail wear. And by the way, if you're wearing the rail, you're also wearing the wheels. So for those of you in the P bar that operate closed loops, it's a system out there, and if one's wearing, believe it or not, the other's wearing. We also learned that in those 5 or 6 examples that a series of multiple perturbations in a row, none of which are singularly condemnable, can directly cause derailments. And that's part of the problem with condition-based geometry measurements. We look at the rail here, we measure cross-level gauge, alignment, surface, profile, left and right rail. It looks good. We walk down here, whatever, 20 meters, we do it again. And then we walk down and do it again. And we take these discrete looks at the rail, and we come back and say, well, everything's great. But we don't look at the resonance that's created by a series of certain perturbations and the distance between them and things like this when we take these discrete condition measurements. Now, the other thing is combinations, okay, not just a series of maybe one type of perturbation, but combinations of multiple situations such as cross-level alignment or profile, again, none of which are condemnable by themselves, can directly cause an accident. Marginal track conditions, which are not condemnable, can cause marginal vehicles to derail. And folks, here's my point. Marginal vehicles are a way of life, okay? Every wagon out there has some kaflugally in it. I don't care. I haven't seen a perfect wagon yet, okay? I've seen good ones, but not perfect. So every wagon, the minute it leaves the depot, it starts wearing. So as it's moving around the system out there, it's getting more and more wear and more parts. But you have to accept this is the reality of our railroad system. Okay, we're going to have worn vehicles. Also learn the importance of speed restrictions and speed conditions, making sure they're in concert with the track conditions that exist. And finally, our current geometry standards may not sufficiently take take into account the harmonic response of certain vehicles at certain speeds operating over certain spacing of certain spaced out perturbations. What else have we learned? Well, we've learned that our current methods of individual measurements and rail at discrete increments may not be sufficient to prevent derailments and accelerated deterioration of our track or rail asset. Our current practice of periodic human inspections, typically in a high rail vehicle running down the track at 15 or 20 miles an hour, coupled with periodic electronic geometry measurements, is still not finding conditions that can lead to derailment and asset deterioration. In every one of those case studies, the track had been perfectly inspected by the humans that went across it, and had been perfectly inspected by the geometry cars, and no conditions were flagged. That's my point, okay? Why? Why aren't we finding this stuff? Well, first of all, I touched on this last night, but humans may not be capable of correlating all the conditions they observe and making the connections, connecting the dots as to possible outcomes. So they might see a alignment thing, but they forgot they had one down here 40 meters back. And they don't put all this together in the human brain like the computer can sometimes do. Human inspection is variable. It's based on skill, experience, and physical condition of the inspector. So I told you last night, if you were there, you know inspectors fit the bell curve. And on top of that, even the good inspectors have bad days and good days. Okay, depending on if they've got maybe an ailment, a cold, or something they want to get done quickly. So human inspections have variability. The interval may be too long to catch some of these rapidly developing conditions. Like I showed you that last example, in 6 weeks, the track gauge went from perfect almost to condemnable in 6 weeks. And so when you operate a geometry vehicle every 2 or 3 months, you may not pick up these conditions. And as I said, track inspections may not be taking into account the variability of vehicle conditions, wheel profiles, and speeds and drawbar forces. So what's needed moving forward? And this gets to the conclusion of my talk, the heart of it here. I think we need to turn more to performance-based risk assessment. That is, taking into account the types of vehicles that may operate over that track, including potential defects, and the speeds that they may operate at. I also think we got to start using autonomous and automated geometry and rail profile measurements that are out there running around frequently measuring all these parameters, or at least a lot of the parameters that we need. I know Monash has, what again, 80 or 90 vehicles, instrumented rail vehicles are operating in Australia now? Yeah, 80%. And they're out there every day. I sat in the room the other day watching one on the V-line moving along, picking up things. We need to feed that data into a performance-based model that can look at how the track is changing. We need a method to combine these continuously updated geometry data points in some kind of semi-automated simulation environment to make performance predictions for a range of vehicle types and speeds. We also have to look at updating possibly track regulations based on this methodology, and I think that regulatory incentives to move in this direction by relaxation of mandated labor-intensive and safety-sensitive weekly inspection. That hit kind of a note with Mr. Marich last night. He took exception to that. But the realities are that as long as you're going to have regulated inspection intervals with humans out there doing things, the incentive to invest in a lot of automated equipment may be less. But if you could get, I'm not saying elimination of regulated inspections, but at least a relaxation of the intervals perhaps, it might be the economic incentive to get us over the edge to move more in this direction. So, what do we need? What else do we need? A method to prioritize activities based on realistic probabilities of degradation and risk. This afternoon I'm going to talk about a study ongoing now in the U.S. on mud spots. Do you ever have mud spots in Australia? No, it's dry. Okay. We've got estimated 50,000 to 100,000 mud spots in our mainline network in America. We can't fix every mud spot. We need a method to prioritize which ones are critical and which ones are the trivial ones. And I'll talk about that this afternoon, but that's kind of what I'm saying here. We need slow orders based on risk, not just conditions. and we need to move away from maintenance-based on pass-fail regulations and more again to a performance-based system, at least to look at it. Can we do it? Yeah, absolutely. I've done it, okay? We've done model studies for a number of clients where we have used these kinds of track inputs from geometry cars on a quasi-real-time basis. We predicted vehicle performance, and we showed them numerous sites that need remediation that were not flagged by regulatory inspections, and we've had great success. It does work, okay? So I'm not talking blue sky here. I've done it. And it's very cost-effective, I think. We need a cultural shift at the railroad and regulatory level as well. We need to eliminate this kind of thinking. And I hear this a lot, and Robbie and I were talking about this also this week. The thought that I'd rather not know about these problems because once you tell me, it means I got to fix something. This notion is prevalent in the U.S. People would say, I'd rather not know than have to react to it. Because once I know about it and then something happens, now I'm really in trouble, okay? So it's sort of the I'd rather bury my head in the sand syndrome than to know what's out there. And we really got to move away from that. That's not a proactive way of managing our infrastructure. We need to realize that new and different data may be needed in our measurements. Maybe we're not getting the right information. We need better data mining. We need corroboration between the vehicle and the operating departments. Folks, it is a system. And I think Mr. Marich has proved this over the years. I've read a number of his technical papers. He talks about the wheel-rail interface as a system continuously. We need to take that to heart. It's just not the vehicle guys. It's just not the track people. It's just not the operations. It's everybody looking at this as a system problem. We need to change finders into fixers. I said this last night. Wouldn't it be great if we could take half those inspectors out there driving down the track in a truck and put tools in their hands to fix these defects instead of finding them? I think that would be a tremendous improvement in what we're doing. Moving from reactive to proactive, and we also need a business model to show that this approach is cost effective. And I think that's where we're way short right now, is showing the economic benefits. How to start? You got to start small, okay? Maybe one division or territory, see how it works, get buy-in from various stakeholders like labor, regulatory, and all affected, your operating departments are all affected. Determine your criteria for evaluating success, and then make your business case to see if it's cost effective to move in this direction or not. It costs money to do this. It ain't free. Okay? We need inspection, electronic data, more condition monitoring and things out there to bring the data in. We need someone to run the simulations. But elimination of one derailment. The fellow showed us that one handbrake derailment. $10 million, was that right? Some person left a handbrake on. See, that's the difference in our industry. The risk of a derailment, it can be $100, it can be $100 million. Look what happened to Loch McGann in Canada. The estimated cost of that derailment is now $3.5 billion, 48 fatalities. If that had been anywhere else, in the woods, probably wouldn't even make the news. Okay? So it's where it happens, when it happens, the speed, all these factors. Our industry has to realize the risk. When we start turning the wheels on a 100-ton wagon, and it's moving down the track at 100 clicks an hour, it's a risk. And bad stuff can happen if it goes off the track. If it goes off the track next to a school, it's one risk. If it goes off tracks out in a mud ball, it's another risk. That's our nature of our business. So, what is this modeling I'm talking about here? The problem is to find out or figure out which combinations of these marginal conditions we need to be aware of that can lead to derailments, and it is difficult with conventional approaches. We haven't had a systematic methodology to effectively use all these disparate measurements in one kind of succinct system or one corroborated system. We've had past approaches and techniques for derailment risk assessment, including neural networks and reliance on geometry, comparison to regulatory standards. Some people have tried probabilistic modeling. Some have used some simplified first-order models of vehicle performance, some very, I call them rudimentary models that can run quickly in a computer environment. But yeah, that was important in the 1990s. In 2017, we have massive computing power. We can do stuff we couldn't do 10 or 15 years ago. We can do it cost effectively. The other big problem is our past attempts at risk assessment don't take into account external drawbar forces and coupler angles. It's another big one. I kind of grew up doing a lot of longitudinal dynamic work because on our railroad we believed if we kept the longitudinal coupler forces low in buff and draft, we would reduce our derailment risk and get the train over the road even with those marginal vehicles. And that is true. We were successful at it. We kept our drawbar forces quite low. But you have to figure out or know, have some idea what those drawbar forces are in a certain area of the track. When you're going up a mountain grade and you have tremendous draft force, okay, you may not tolerate the kind of geometry perturbations you can tolerate on the flats where the drawbar force is low. Or when you're coming down in grade and you're in compression, again, same thing. You may not be able to tolerate certain things. So we must take into account all relevant risk factors, our measured track conditions, possible and likely vehicle conditions, the most likely predicted in-train forces that are going to occur along the section of track, and the speeds and the types of wagons and marshalling the wagons that we got to deal with. We have to also create a relevant magnitude of the risk factors and the probability of factors occurring at some point in time or some point in the track. Looking at all this stuff, again, as a comprehensive system. So the future simply is this. Use of an engineering deterministic simulation model like Vampire, New Car Synpack, Universal Mechanism to predict actual vehicle performance over a route using the measured track parameters that we just received from our autonomous system at various speed regimes and with the predicted drawbar forces for that area of the railway. So plugging all these components in, the external drawbar loads, the vehicle types and conditions, the relevant speeds, and the geometry that is measured out there on that section of track. The next step is to compare the actual applied L over V ratios to the track and wheel set against the calculated threshold for wheel climb or rail rollover. And let me just get to that real quick. I'll step back. We have to understand that some areas of the track have a lower or higher threshold of derailment than others. If we look at the two main outcomes from drawbar or from wheel set forces, at the top you have wheel climb. Wheel climb is classically defined as the Nadal ratio, and the parameters important in the Nadal ratio are gauge face friction and the gauge face angle, or the angle between the wheel and the rail. Those are the two important parameters that go into the Nadal equation. And so if you lubricate the high rail and you grind it properly and keep that angle fairly perpendicular, your threshold for derailment will be extremely high. If you let that rail get extremely dry and you let that gauge face angle have a significant slope to it, you're going to have a high risk of wheel climb. And so how you maintain your rail in a given curve sets a threshold or a bar. Okay, think of it as a fence. So the better you maintain, the higher the fence is. And if you do poor maintenance, your fence will lower. And you get too low, many wheels will jump the fence and derail. So, and the other thing that can happen is rail rollover. And rail rollover is a function of top of rail friction, the base to height ratio, rail camp, and gauge conditions at the site. So again, for rail rollover, we have similar parameters that we have to be aware of when we assess our track conditions. So, in this section of 10 kilometers, are we lubricating? Are our lubricators working? Or have they been turned off for 10 years? And that will tell us right there a risk factor for rail rollover. Do we have canted rail? Do we have differential cutting, where the base of the rail on the outside is down lower than the inside? Pre-existing rail cant? That sets you up for rail rollover. That would lower the threshold. So with geometry cars measuring rail cant angle, high-speed turbometers measuring friction, you can throw that data into the model as well. Let me step back two here and say, the question is, well, how do you get longitudinal forces? How do you know? There's two ways. One, the car that Monash has measures drawbar loads, right? So you get a real-time sense of what are the real drawbar forces we're seeing along the track at every interval. That's a great way of doing it. Or you can use a deterministic simulation model like TOS or TOES. Universal Mechanism has a longitudinal factor. I was talking to somebody, Ian, where we were talking at break. I have some reservations about it currently. I think it will get to a more refined point in the future. So we have tools out there that can predict the longitudinal forces. Also, on the dynamic simulation side, we have models. Vampire, Synpack, Newcars, and Universal Mechanism are the big four that are used worldwide. There's a couple smaller ones we won't talk about. But what they do is simulate a particular vehicle-track interaction and wheel-rail interaction on those things, and it outputs vertical and lateral wheel loads and L/V ratios as a output of what you put into it. So the concept overview is this. Compile the data that characterizes your track using track geometry card data and other sources, your rolling stock through wayside detection, and your operating parameters such as speeds, forces, operating practices, etc. Enter all these characteristics into a computer model that can develop dynamic L/V thresholds, develop the most probable applied loads laterally and vertically, and use these simulation models to predict the actual performance of various vehicle types along that route under different load regimes. And that will provide you then with a derailment risk assessment and can also be used for maintenance planning and remediation. If you look at the universe of derailment causes, there's 5 or 6 big buckets there. And we're talking about data kind of on most of these actually. We have derailments due to excessive drawbar forces. We have derailments due to various track geometry-induced causes. We have track integrity-induced causes like broken stuff, broken fish plates, broken rails, broken frogs, things like that, stuff that breaks, okay, catastrophic failures, which often are driven by stuff here. We are learning, there's been a number of research papers in the U.S. where researchers have found a direct correlation between geometry defects and broken rails. Because when you allow the rail to start bending a lot up and down, you cause the small incipient cracks start to develop. Now people say, wait a minute, Gary, when you bend the rail down, you put it in what? Where defects occur most likely in the rail, by the way? Where do you find most of your defects? In the head, right? At the top of the rail. Detail fracture, transverse defects, verticals, etc. They're in the top. That's where most cracks develop. Oh yeah, we get some base cracks, but 95% of them are in the head of the rail. So when you push rail down, is the head in compression or tension? Compression. Do cracks grow in compression? Now why the hell do we have cracks? It isn't this that causes them, it's the wheel coming in and it's the upward bending moment that rail experiences if it's not adequately supported. So you watch dynamically a piece of rail as the wheel comes in, and it goes down, but it's also doing this. So you get a negative downward bending moment, you get upward bending moments as well. It's those upward bending moments put the rail in tension that can develop crack growth, okay? And we see a direct correlation in geometry and causation. Mechanical condition is another big bucket of causes. We need to know typical conditions on the equipment. As I said, other kind of catastrophic failures through weather, inclement things, etc. So we got to take all these causes into account in our modeling to make sure we incur. So here's a block diagram of what I propose, basically. What it is this. We will gather track data with our various collection methods. We will also gather vehicle characteristics, and we will develop an L/V derailment criteria or threshold based on the equipment and the track. We will also use some kind of operations data or toes prediction to get drawbar forces. We'll also put in our speed limits, and we will throw this data into a vehicle dynamics model like Universal Mechanism or Vampire, and we will simulate these vehicles over this track at these force levels with these speeds, and we will get a predicted risk or L/V risk along the route, and also a maintenance database as well. So you can say, what are some of those sources of data? This is just a universe of some of the things we have at our availability now. To characterize the track, we've had track geometry cards for years, putting out data every foot along the way. We have rail profile and cant measurements now. We have high-speed thermometers for friction. We have gauge restraint measurement systems that apply loads. Are those used much in Australia? Don't use those? Well, they're both effective on wood sleepers, and if you're predominantly concrete, you have lesser value of them. but they're very good on wood sleepers to find. By applying a continuous lateral load of about 14,000 pounds, we can predict the total gauge restraint of that track. The Yamrail deflection car, I'll have some things this afternoon to say about that. The type of equipment that Monash is doing with instrumented rail vehicles, providing continuously updated geometry data, portable measurement systems, track charts, and machine vision systems. These are all things that are out there right now. We're all collecting them, but they're not being used cohesively, okay? Some people look at machine vision, some people look at the geometry, etc., but we're not using it in any kind of integrated fashion. The result of that would be a computer prediction of the track geometry, vertical profile, lateral gauge, crossover, and curvature along the route as our input data. We also have to develop our thresholds, our characteristics of the probability of wheel climb at a given spot based on the Dow equations, or the probability of rail rollover along the track based on rail cant, lubrication, and things like that, fasteners, unloaded, delta gauge, all those kinds of parameters. So we need to come up with our thresholds, at least in 10-foot increments, and then we would simulate L/V ratios to either predict extreme risk or high risk along the route. So these would be an example of setting up our threshold barriers and say, well, as we move down the track right here, we need an L/V for wheel climb over 2.0, but in this area, for some reason, it's 1.5. In this area, it's 1.75. So we would essentially draw a line along our track structure of our thresholds and then compare the predicted results against them. On the vehicle side, we've got all these data points coming in from machine vision, truck performance, wild systems, wheel profile systems that characterize our vehicle fleet out there. So we can use this data as well. And put them, I won't waste time on here. Also, we need to put in the various drawbar loads as these trains are going up and down grades. This is one train, by the way, winding its way up a grade. It's kind of an interesting picture with mid-train power. And I'm getting to the end here. I just want to show you the net result is this. So we have a predicted threshold along the route of wheel climb, and we have a predicted applied L/V along the route, and it's pretty okay along in here. We see one place here where we have a high spike. So we have some, I would call low-risk areas here where we're exceeding a low-risk threshold, but then right here we have a very high risk. So that's an area that would need a message alert sent out, a high-risk area that needs immediate remediation. The other three areas just might need to be tagged for planning down the road. And I'm going to skip a couple of these and get to this final slide. I think I've got just a few minutes. Yep, 2 or 3 minutes. How to start? I would say if you're going to do this, start small. If you're in the passenger business, take a route maybe, or if you're in a captive fleet, take a particular territory. Just start with track geometry car records and maybe 5 car models. Don't try to do this, you know, it's the old saying, how do you eat an elephant? In small bites, okay? You're not going to swallow the elephant whole here, but if you're going to start this and start looking at it as a tool, start small. Take one territory, just start with track geometry. Don't worry about rail friction, rail cant, profile. That can come later as you get more experience. And then maybe start with a couple car types, a flat wagon, an ore wagon, a passenger vehicle, whatever you typically run. Start with your track speed limits as they exist. Assume some nominal drawbar force inputs. If you don't know what the drawbar forces are, start with 50,000 pounds, okay, along the route. Just say, okay, assume we got 50,000 pounds. At some point in the train, you will probably have 50,000 pounds on a typical train. So apply this data, assume some typical values if you don't have what's missing. You know, I was always amazed by young engineers. I hired a bunch of them over the years, and they come out of school, man, they can run spreadsheets and everything, they're whiz bangers. But then you give them a problem to solve, they come back and say, well, I don't know what the friction is. I said, well, assume something. Well, what do I assume? Use your brain, okay? Young engineers need to understand it's not what you know, it's not what you know, it's what you don't know and how you get there, okay? It's how you fill in the blanks. When we do engineering work, we have to make assumptions all the time. We don't know every parameter in the real world to a high degree of certainty. What separates to me a good engineer from a bad one or a poor one is the ability to make measured assessments and measured assumptions on things that we may not know. And the same is true in this process here. Some long-term obstacles to doing this, rail coefficient of friction changes daily. We know that. So you might measure it today, it may change 50% tomorrow. We need increase in our technology, more frequent track geometries, and autonomous measurements such as the IRV. We need more widespread deployment of turbometer systems, track modulus systems, gauge restraint, mechanical wayside, etc. And our increased computing power and data management capabilities are there. We've got it, we just need to know how to use it. And finally, we need to think about our culture, change of how we look at this stuff. We need to quit worrying about finding, say, don't tell me I got a problem, to the culture of, yeah, I want to know where I have a problem so I can prioritize its maintenance to eliminate the risk of derailment. So to finally say, I think there has to be a better way, okay? This is a picture I shot about a year ago. I was told to inspect some track, and I got in the truck, and we're going down through the weeds. I'm going, what the hell am I doing here? There's got to be a better way. I think at least we can start thinking that the purpose of my talk today was sort of to ignite an idea in you that maybe we can start doing some of this to move from a strictly regulatory condition-based system to more of a performance-based of how actual rail vehicles and actual operating regimes are going to perform over those perturbations in the track that are not being flagged now, but they could have an underlying risk factor associated with them. So, the end, we hope, of accidents like this by using some of these tools and techniques. And I'm right on schedule, Robbie. Very good. Thank you. I'll take Brandon's next.
Thanks, Gary. I think we are right on schedule, but we don't have time for questions. So if you're happy, we might roll for your questions.
We'll be around at lunch or something.
Lunchtime or also
Yeah.
the session. So thanks, Gary. So next speaker is Philip Campbell. He's from Australian Rail Track Corporation. So Philip is the acting Executive General Manager of Enterprise Services for ARTC and has over 38 years experience in engineering, maintenance and project management. Philip holds a BS degree in mechanical engineering and MSc in structural design. He's a fellow of engineers. He's a fellow of the Engineers Australia and a member of the RTSA, and was awarded the Order of Australia Medal in 2013 for services to engineering.
Thank you very much.
Thanks, Phil.
Well, how do you follow Gary there? That's the first question. I'll move over to ours. One of the first things, this is the general areas we're going to look at covering in the talk. We're looking about the issues of safety, ride quality, and degradation of track components. Before we do that, though, I've just got a couple of comments. If I said to you that a ship was seaworthy, or that an aircraft was airworthy, you'd have a pretty good idea of what that means. So what's the rail equivalent? What's railworthiness? It's not a term we often use. I've got a definition for you, just to see what you think. What I've done is I've taken the definition of airworthiness and turned it into a rail context. And it's got to be a system definition. So we say it's the condition of the rail system, its suitability for rail operations, and that it's been designed, constructed, maintained and operated to approved standards and limitations by competent and authorised individuals acting as members of an approved organisation whose work is both certified as correct and accepted on behalf of the rail system owner. So we've got to think from a systems perspective about the way that we look at all of those aspects. The maintenance is not alone. We have to make sure it's within that context. So I'd certainly be interested in comments later on how that definition fits with our regulatory environment and also with what it means for our maintenance. The other thing I would like to talk to you about is with regard to new technology. It's quite a bugbear of mine that people use that term and flip it around without really giving it an engineer's approach. We act like members of the public when we talk about new technology often. How mature is a technology? So what does maturity mean for a technology. You could say one definition I've seen for maturity is an evolution that has removed or muted undesirable consequences. So in terms of an engineering approach to adopting a technology, they tend to manifest themselves in products. And a product is a particular embodiment of a technology with certain features for a specific purpose. So I think as engineers in the rail industry, we need to be scanning the environment, because not all of the technology is going to appear in this industry. It's going to appear in the aerospace industry. It's going to, autonomous vehicles. So when we look at maturity, you take your phone out of your pocket. Is that more mature than an autonomous vehicle? I'd say probably it is. So how mature is that technology you're looking to adopt as well? When I first started at Monash, we had one computer, which would have been the size of this room. Who's got a computer in their pocket? How many, in one stage there was one laser in Australia. How many lasers are there in this room right now? Every hard disk drive, the mouse, there's lasers, many lasers in this room. So when we think about technology, we need to just think about how we can adopt it. And Gary made the very good point that the adoption of that great computing power now is the way to the next phase. And I strongly actually support what he has said about the idea of being able to, almost in real time, be modelling your track. I mean, the two key issues I've got for Gary in that regard is how do you set those limits, and then how do you apply them locally where they're way below the normal safety limits for your railway. So that's a challenge for us, I think. Okay, I'll move on. Picture of some of our double stack traffic going to Perth. The point I wish to make is several years ago that traffic was different. It wasn't double stack. In a few years' time we'll be running double stack from Melbourne to Brisbane. So you've got to be most aware of what's happening with your traffic. So you're maintaining your railway to the standards that you have, but if the traffic's changed, the axle loading averages have changed, or the issue of whether the double stack traffic, for instance, can cope with the cant you've got, the condition of your track geometry, you need to be very linked with your commercial people in terms of what's happening to the traffic on your railway. Besides which, it's a good photo. Not quite as good as going up the hill, Gary, but it'll have to do. So the first thing is the application of safety, obviously, and in Australia the way that we've tried to approach this is to get engaged with RISB and to be involved in the development of the track standards that the industry takes on board. Obviously the rolling stock standards, the wheel rail interface, and also then start to align our code of practice with the RISB standards and basically adopt the RISB standards. But once again, these are safety standards, and Gary has pointed out obviously this morning that by itself doesn't always guarantee safety. One of the other issues is ride quality. We get a lot of press in Victoria about ride quality. We meet our safety standards for our railway, but in terms of what's acceptable ride quality and how it deteriorates over time. We're currently running around with several of the ENSCO VTI units that are fitted to some Pacific National locomotives that are providing us data on the track. And with that data, it's helping us to pinpoint areas where there are high accelerations, but in terms of having actual limits on that acceleration, it's very hard to say what should be the level of acceleration that is unacceptable. We have track geometry car going around, but when the VTI unit goes round, it may not always show a fault at the same area as the track car, and the variation in the level of the fault varies sometimes with speed and other conditions. So it isn't a simple matter just to say there's an easy threshold for your figures. We've got several of our coal trains in the Hunter Valley that have got the Monash system fitted to them, and analysing that data in that closed system But I get more concerned with our interstate network where there's a wide variety of rail traffic. It's not a closed system. You often get offset loads and the condition of the track varies significantly. In fact, I often use the analogy to people. Imagine you're on a windy day out in a canoe and you stand up in that canoe, right? You can imagine yourself standing up in the canoe and you're holding a basketball, right? You've got your basketball and you've got a marble on top. And your job is to keep that marble from rolling off that basketball. Okay, can you imagine yourself doing that? Well, the analogy back to the railway is that the day your railway is manufactured, that marble is right on the top of that basketball. It's in its best condition, and as soon as you start to utilise the railway, it starts to deteriorate. Now, you can let it deteriorate a little bit and get that marble back to the middle, or you can let it run right off to the edge. And the effort to actually recover that marble and stop it falling off is huge. And the issue we have, if you like the analogy, is to say there are parts of our track where we only let that marble deviate a little way, or the condition of the railway, and then we bring it back. In other parts of our network, we let it deviate quite a way, and we bring it back not to the same point. And they're both acceptable maintenance regimes, but you've got to decide which one you're operating and is it fit for purpose. So what's your canoe there? So at the moment what we're doing with the Ride Quality Index is we're doing some work just to determine can we use the ENSCO VTI data to come up with a acceptable ride quality index that we can use to trend ride quality over time. In terms of degradation of our track components, we're obviously managing the safety limits. We use top moving sum there, which allows us to accumulate the values over 50 metres of track in half-metre limits, and we have a nominal value of 300 on that we use for looking at our top degradation. I guess one of the other things we also want to look at are issues like corrugation, which sets our rail grinding priorities as well. So in terms of initiatives for improvement, we want to try and align what we're measuring on our track geometry car to try and get alignment with the VTI data. As I said, when you map them against each other, they don't perfectly align. We also try and get access to alternate standards as well. We subscribe to the Network Rail standards in the UK, and we keep abreast of what's going on there as well. We also try and look at what's happening elsewhere in Australia. Some other rail infrastructure managers are very free, like us, in putting our standards out on the internet. Others keep them behind very closed doors. So I'd encourage all rail infrastructure managers to make your standards available to the rail community. I'm finding there's some good stuff with PTA in Perth, for instance. They've got some good recent work they've been doing. So certainly look at others, and I encourage you to make them freely available. Here's an example of some where we tried to map some track faults against the VTI data. So the VTI is the green trace and some faults from the geometry car. And whilst there's some elements of complementarity there, it isn't a perfect match. And there's a number of factors that become involved in that. If you run it at a different speed, you might get a better match. So one of the issues with a ride quality index is to say, how does that relate to your track geometry, and how do you get the feedback that Gary was talking about if you're able to simulate that, and how do you change your geometry limits based on the data you get from traces like this. So I've tried to keep it brief to allow time to talk about some of these issues, and if anyone wants to, I guess, also relate back to the work that Gary did and some of the initiatives that he's put forward, that might add to our workshop discussions.
Questions? Yes.
I'm glad you mentioned subjects of sorry, Alex Q from Queens and Rail, but
Alex, you might want to stand
yeah,
up,
sure,
because
sorry.
people are saying that the questions are not being
sorry.
read at the back. So yeah.
So Alex Q, currently at Queens and Rail, formerly of Network Rail and rail track and British rail. So I know a fair bit about cycling top. And the one thing that worried me was 20 years ago, I can actually remember teaching inspectors how to identify cycling top. It's a bit of a worry actually, and it's probably interesting. Last night, Ravi, you mentioned the link up with Warwick University. That as an industry, we haven't shared our knowledge across the world. I didn't know when Gary's example was from. He called it was a multiple implementations, but it's good to see ARTC looking at cycling top. And also the next level after that was actually identifying, whilst you know what cycling top is, how do you fix it? I know a bit of the answer to that. I remember doing a research project, I didn't say 20 years ago. It obviously goes into the bin and then it comes out. But I think there's something for institutions, both academic, Warwick and here, and actual rail organisations to share their knowledge. So.
Well, I think John Paff made the point to me yesterday. He said setting a set limit for cycling top, you don't believe actually works. I think the idea of being specific to a location and saying to people that this particular type of cycling top at this location doesn't work, but to publish a single standard for cycling top, I think would be very difficult because it won't apply in all circumstances.
It's worth saying, so the research I did a long time ago was actually take a smaller motor vehicle and record in both directions on the site to try and identify not just the cycling top, so not just the resultant, but what often is caused by the discrete defect at the beginning. So you take away the beginning, the rest is to come. And we were looking at coal lines, high-speed 200 an hour passenger lines, all different scenarios. So I'm assuming that rail's pushed that on. I've been here a decade now, so at some point in the last 20 years, but I don't know. It's one of these things about sharing knowledge of academia and in the profession.
John, do you want to make any comment on that?
My comment, just a bit on the subject of cyclic defects and combinations of defects in general, which is a very hot and topical subject. The problem is, every vehicle responds differently. Every vehicle has a different wavelength that it's sensitive to. And it depends on its loading condition, it changes again. So. Oh, hello, look, I'm famous. No, my point is every vehicle responds differently, and there is no single or small handful of cyclic defects or combinations of defects that are hazardous and nothing else is. It's anything is potentially hazardous. So just strictly looking for a strict set of combinations of defects, whether it's cyclic or otherwise, I believe is a bit of a dead end. What Gary said about getting actual track and simulating actual vehicles is a far more productive path to take, because you don't have to predict in advance what combination of defects might be hazardous. You can actually check the real track. That's what I was talking to Philip about yesterday.
Are there any other comments from the floor on that in terms of that concept of real-time measurement and remediation that is unique and specific?
No, I agree. I think it's a fantastic idea. It's just wondering how many solutions you end up with, how you filter out the forest from the trees. No.
And then there's the question, what do you fix?
Exactly.
Yes, I've got a defect, but what am I going to do about it?
Yeah, thanks. The speaker, who's from British Rail, I didn't, or Network Rail, I didn't catch the name, but the feedback we've got from the UK Network Rail guys is that you really need to find the initiator. And if you can find that and fix that, you've solved the problem. That's the point you made. So it's early days of getting information from the UK, because our cycling top will be different speeds, different rolling stock. So we'll have to adapt there rather than just simply adopt it. But we're hopeful.
I would like to make a comment. I think I don't want to steal Graham's thunder, because I think he's going to present after, so probably he'll cover some of these. But I think the approach Gary is presenting and what you are agreeing is actually quite interesting, because I think that's what I think in certain aspects the Monash has taken on to look at that particular, identifying how the track is performing under various, the perfect storm. I think under certain operating conditions, how it's actually performing and picking up, not when it's actually going to derail, but well before, so that you can actually start planning your maintenance. But I'll leave that, yeah.
And I guess we do move away from time-based periodic maintenance in that you're going to more of a reliability-centred approach. If there are some things that are stable, then you don't do it. If you're going to things like drone inspections, then you can substitute those sort of things for your weekly track inspections. So people having a mindset of, it has to be done every 90 days, I think that has to end. But you have to have the data to support going to reliability centre maintenance.
Thanks. Thanks, Phil. So
you might need that one,
yeah,
because I think it's done here.
okay. We're I'll go over here. We're running a little ahead of time, which is good. We can always use that. So I just want to reinforce a couple of points that came out in that presentation. One, the importance of sharing information across jurisdictions. So today we're hearing from Gary from the US. We've heard from people with the UK experience. Philip mentioned that in his presentation. He also mentioned that ARTC published their standards and it's basically open. Not everybody does that, but I think a way to facilitate the sharing of that information, both with your related organisations in Australia, but internationally, is very important. And so today is sort of facilitating some of that sharing in a way, but I think it can be improved. So we'll move now on to the next speaker. So next speaker is Graham Chew. So Graham's with the IRT here at Monash. He's the research manager and has over 35 years experience in railway engineering, including track and rolling stock performance, design and condition monitoring. He has a master's degree in structural engineering and is a member of the RTSA, Engineers Australia and the Australian Rail Standards Committee. Graham is a recipient of the ATSE Clooney's Ross Award and the RTSA Individual Award. So please welcome Graham.
But it's been a fair while since I've been dabbling in track geometry per se. At the outset of my talk, I guess there's one thing that I'd like to, I suppose, open up the discussion throughout this presentation, because I recognise that you guys out there are actually the experts. You've written the standards, and if I start to comment or question or challenge some of the standards and how they're being used, I'd really appreciate being shot down and say, no, we're doing things much better than that, because what I'd really like to achieve at the end of today is what does best practice look like? That's really where I want to try and get to in terms of any of the discussions, be it through the use of just existing track geometry data, who's doing it better than other people. But not only that, and you'll all obviously realise that Monash University has been developing the instrumented wagons over the last 15 years. 2002, we put our first one out there. Steve Marich mentioned yesterday about 15 years to embrace new technology, make it mature. Well, we're starting to get almost there, I'm guessing. Use of big data. These are the other sorts of things that are being talked about in the way of doing things better into the future. Gary made the point. A young engineer can't use a ruler, but they can damn well use a computer to manage data sets a lot better. So these are some of the things that we want to talk about through this presentation, sort of both now and later through the day. And I guess the other point that was made last night was obviously there's no gaps in the RISB standards, and I think that's something else we'd perhaps want to challenge throughout the day, just to see if there are better ways of doing things. Anyway, let's kick on. That's me. So what we want to talk about today is some of the track geometry standards. I want to briefly touch on things like RISB, look briefly at ARTC standards and just how some of these things are being used, what new things are they introducing, and what might be the limitations. And again, I'd really welcome conversation, discussion throughout the course of this. Want to also move on to things like new cars, Vampire, how we can use these types of tools to better assess the condition. And a lot of this has been touched on already throughout the course of today and last night. And then the last point is the alternative methods for collecting this track condition data. And as I say, what I really wanted to, sort of from my perspective, is to understand how track geometry data is currently being utilised with the objective of determining best practice, whatever that may be, and to introduce new technologies being used to assess track condition and determine how these may complement current methods and how we can get those into the operations. All right, I wanted to start with a bit of history. 1986, I wrote a paper for the Heavy Haul Conference in Vancouver. It was called The Application of Computer Modelling to Track and Vehicle Maintenance Practices. Discussed the development of a model to optimise track maintenance planning. You wanted to look at track deterioration rates. You wanted to know, when should I go out there and tamp my track? The model was developed in conjunction with Mount Newman Mining, Hammersley Iron. They were really keen on wanting to understand, when should I go out there and maintain track? Is the current standard too good? Is it not good enough? Now, this is what we wanted to do. This is 30 years ago. Question is, how far have we advanced and what are the major reasons that we have not achieved this objective? Does anyone believe they're actually doing that right here and now? Do they have any idea what optimum track might look like? How it might be measured? Interested to know. And certainly 1986 certainly wasn't the first paper around talking about this stuff. There are a lot. So what did the model try and do? The cost of running the railroad was in part related to the condition of the track. That I don't think is an unreasonable statement. In this case, what is the optimum track quality? What's it depend on? It depends on how quickly that track's deteriorating, the types of vehicles that are running over it and the maintenance. What are the costs of operating that railroad? How effective is your maintenance going to be? All of these things are going to determine what the best looking track is going to be. So we developed a computer model that tried to optimise tamping and lining cycles based on track deterioration rates. It looked at the potential cost of derailments. If my track's poorer, am I more likely to derail? What's the cost of fuel? Am I going to have to grind my track more often? What's the cost of wheel wear? What's the cost of rail wear? Am I going to get more rail defects in the track? This appeared to be a totally rational strategy to understanding how to best manage your asset. A couple of questions I posed there. The optimum varies. For example, and I guess it's a question to all of you maintainers out there, if track is poor but showing no signs of deterioration, should I go and maintain it? Should I just leave it alone? Often you'll put a tamper through it and it gets worse. Often bad sections of track always remain bad no matter what you do, so why touch it? Should the same track standards apply to sections where, or areas where trains go slower? But there's a whole bunch of different questions that you can pose along the way to try and work out, for any particular track section, how should I maintain it? And so we wrote a model and we were pretty proud of it at the time. Well, I was proud of it at the time. Trouble was, why did it fail? We never managed to implement it. Reasons being, computer systems were inadequate to store the required data. Back then, 1986, computer systems were pretty fledgling, and to try and, I've listed a bunch of information for every 400 metre track section. We wanted a whole bunch of information to be stored away. What's the chance of that happening in 1986? What's the chance of that happening in 2017? point 2 there I make, the ability to maintain accurate data for each track section across the rail network was limited, particularly if required in a single database. Now, I don't suppose railroads these days would have a bunch of Excel spreadsheets sitting on individual people's computers, not necessarily linked to a main database somewhere, would they? They'd all be in Ramsas or, you know, just wouldn't happen these days. Yeah, right. So can we actually achieve this type of stuff? Bottom point there, track geometry data was not collected frequently enough, nor with sufficient repeatability to allow track deterioration rates to be established. So there was another fundamental flaw in the model. We simply couldn't get enough data into the model to try and optimise or to predict track maintenance. And forgetting about, you know, scheduling of your tampers and all of those other things that, you know, that you would obviously need to do. You know, you're not going to, you know, so I'm going to optimise this section and do it every 32 million gross tonnes and that section every 45 or whatever it might be. But it was the start of what seemed to be a reasonably sensible process. But, you know, question, is it reasonable? I mean, do we need to understand this stuff, or are we happy with what we've currently got? Why do we do track maintenance? Effective track maintenance is required to maintain the track geometry throughout a rail system to ensure the safe passage of rolling stock. I mean, there's thousands of different definitions and reasons why we do track maintenance, but effectively what you want to do is maintain a platform whereby the vehicles that run on it safely. Irregular track geometry is undesirable because it leads to a whole bunch of problems, and we've been talking about those today already. So, again, pose a question. Track geometry recording cars, been around a long time. How many of the organisations here today are in a position to trend track deterioration with their track recording cars and use it for short to medium term maintenance planning? Good. What sort of time frames are you looking at for projecting forward? Okay. With a frequency of recording of? You think that's good enough? No. Yeah, okay. So, yeah, and again, we ask the questions. How often is the data collected? How does the frequency of data collection compare with the maintenance planning horizons? Lots of track recording cars are run every 4 months. Is that good enough? You know, it depends on your track deterioration. It might be 6 months, it could be 12 months. I think the most frequent I saw was perhaps in the US on high-speed lines, they're talking about 2 weekly. Numbers like that, whether that's right or wrong. And then the fundamental, one of the other questions is track geometry data in its raw form, or depending on how you choose to manipulate that data, a good measure of track condition? Not sure. It's one measure.
Any information depends on what you do with it.
Yes.
It's the sole point of truth in treacherous waters.
No, that's dead right. It depends. Are you using it as... No, track geometry data gives you a perfectly accurate representation, spatial representation of where the rail is. How does that then relate to some of the, you know, track condition in terms of vehicle dynamics and responses, and you use standard deviations or peak levels of exceedances and all of those? We all know that the standard deviation of the track geometry parameter is probably a very poor representation of the condition of the track. How many people use a TQI that's a sum of multiple standard deviations of track condition? Again, maybe I'm out of date, I don't know. I'd love to understand or hear what people are currently doing with the data, and let's understand what best practice might look like. I just want to briefly touch on a few of the standards that are sitting there, and again, we're probably already starting to talk about some of this. AS 7635, 2013 is the current RISB standard, I'm led to believe. It does specify track geometry standards for design, construction, commissioning. There are maintenance, I think, intervention levels in there. So one of the comments I think, Ravi, you asked earlier, are there recommended standards for maintenance? They do start to get introduced through these standards. But they make a comment, where combinational defects are detected, these should be investigated and reviewed by the rail infrastructure manager. I hope the rail infrastructure manager is comfortable with looking at these combinational defects and making the decisions about them. I'll ask the question. Provides recommendations re-cyclic top, so it starts to introduce the, we talk about cyclic top. Basic design parameters for various gauges, construction tolerances, minimum track geometry, recording car inspection frequencies, and my understanding is that's 4 months on the mainline interstate corridor. Again, a lot can happen in 4 months, and I'll show some examples either later in this presentation or in the one later this afternoon on just how quickly your track can deteriorate. And I know Gary touched on it previously in terms of the effective gauge. Up in the Pilbara, heavy rains, or Hunter Valley, heavy rain. Your number of severity ones that we actually record probably goes up by a factor of 4. There are other ways of detecting them. Anyway, go back to this question. The RISB standard provides response actions based on peaked measured geometric irregularities. E1 action prior to the next train. That recording car is running once every 4 months. And then all of a sudden, before the next train, do you have to go out there and fix that piece of track? What happens for the other 120 days when the track recording car isn't out there?
Correct. People are of the misunderstanding that the only way to measure track is through a track recording car.
Correct. And then we do talk about there are multiple levels at which you are, you've got you've got inspectors out there and a whole bunch of other things. But again, it's a very, so once every 4 months we'll stop a train because we found an E1 defect. Who's defined what an E1 defect should be? There's a table in the RISB standard which says, for this class of track, this axle load, this speed, if I get an exceedance of such and such, I have to stop a train. Who's assessed those standards? Where have those numbers come from? Does anyone know? Are they right for your current rolling stock? Rolling stock's changed. I mean, Phil just made the point. We're now running double stack containers. Are they any good, these standards? I don't know. Let's run them through a simulation model. But the thing is, 1 exceedance, 2 exceedances, 3 exceedances, cyclic, combination of cross-level with alignment, with surface, with twist. Again, we all have these standards sitting out there, but are they the best thing? I asked the question. ARTC, and Phil's already touched on it, very similar to the RISB standards. I tended to pick up the tolerances may be different, slightly different to RISB, but it could come back to things like the chord lengths of measurements might be slightly different. I wasn't sure. I certainly haven't drilled down into the standards, and again, for those people who are here, please comment if my understanding is wrong. Use track geometry calculations, standard deviations over 100 metre lengths, not uncommon. TQI distributions calculated, and I think again, they're just effectively you want to have your bell shape or your distribution of track to be better than the specification that you've got in place. One of the things that it did appear to talk about was the repeatability and the measurements and the accuracy of the measurements. And Phil, I'd be interested to know how you go about doing some of these in terms of how often you assess the repeatability of your recording cars, because I know when we were doing the work back through the 80s, you know, I've done 4 or 5 sets of repeatability trials on recording cars, and one of my concerns has always been how much variability you got. Now, clearly systems are better now, or we hope they're better now, but it is very important that people chuck a recording car out there and have this absolute faith that what's coming back is correct. You know, to me that is a really important step to understand how good your car is and how reliable, especially if you're trending the data. You know, there's a smirk. I'm not sure what that might be. Care to comment?
We'll leave it for the questions.
So, don't ask me the questions. And geometry data is used as one of the inputs to maintenance plans. Is that any comments?
We do repeatability each year.
Yep.
Not each run, but each year we do repeatability runs.
Yep. So forward, reverse, all of these sorts of things, yeah. No, that's exactly, it certainly has to be done. Queensland Rail, I mean, again, I've only touched on a couple of the points because I don't think your standards are available to the wider world as we discussed. So, and this is what you commented on before. There's a comprehensive range of inspections. You know, it's not just about a track recording car going out every 4 or 6 months. It's the fact that you've got the high rail patrols and again, you use things like track condition index, limits probably similar to RISB, those sorts of numbers, or you've got your own set of standards. And yeah, you do actually take it a couple of levels further in terms of, you know, cant imbalance, lateral jerk, and I know that's something that you're quite keen on.
You should answer your question, Graham, which is to say that OTCI, we don't use it to proactively manage track because it is very much seen as an average, but it is what's governed.
Yeah.
We're contracted. However, the other ones in there, we have used them in the way you describe. You use your knowledge.
Yes.
And seen a reduction from over 500 to almost double figures in the last 3 years.
In terms of
The twist gauge, alignment, everything else is specified. So
yeah.
actually, if you just challenge, that's the answer.
Yeah, okay. I had a brief look at a couple of the other standards. EN 13848 is the European standard. It looks at each of the individual parameters, so again, gauge, cross-level, twist, surface, alignment, and provides guidance on resolution and measurement uncertainty. And I've recently been doing some work on a new Mermec machine, and yeah, again, it's very much driven by some of this type of information in terms of, you know, when you're doing the repeatability trials to look at how good the data is. It also requires you to look at the different frequency bands. I mean, again, the criticism we make of standard deviations is that it lumps everything. It doesn't really tell you anything about the dynamics of a wagon. But if you start to do spectral analysis of your geometry, at least it can start to tell you whether it's feeding into the critical wavelengths of your wagon from a response perspective. And I'm not sure whether anyone here is really looking at frequency content of the geometry to any great extent. Combining standard deviations suggest calculating standard deviations of combined parameters. Now, we talked about combinational errors. So they actually sort of start to hint at adding, and this is my understanding, you sort of add your alignment and cross-level errors, or whether you subtract them, I'm not sure what the best combination is of some of this stuff, and calculate a standard deviation based on these as another measure of perhaps trying to understand combined errors. And I think Gary probably hinted at some of the very basic ways in which this data can be used. Sort of, they use point mass acceleration, so they try and work out where the centre point of the wagon's likely to be, and have a look at how that would move as it's going down the track at a speed, to give you some sort of measure of condition. How good that is I don't know. I mean, there's much more power now in your computers that you don't necessarily have to just be doing that. So continuing on, provides commentary. It does actually start to bring in the concept of instrumented revenue vehicles and alternative ways, even though it doesn't talk about what the options are or how to do it. It certainly says that, and I think the words it says, both from a safety and ride quality perspective, this is a good path to be heading down. Makes a lot of sense. Suggest calculation of signal PSDs, so the spectral content of your signals, to allow manufacturers to have better knowledge of the track they're running over. For infrastructure managers to know how defect wavelengths or what sort of defect content there is, wavelength content there is in their geometry. I think I've sort of stuffed up the words there, but fundamentally we want to understand what the frequency content is. Vehicle response analysis. Now this is something that I think both EN standard is starting to look at, and the US is starting to look at, and I guess it's almost a poor man's. I won't say that. Sorry, Natushan, if you're here. He's doing some work in this area. But what you're trying to do is relate the geometry to the performance of a wagon. So you go out there, you measure the response of a wagon to track geometry data. You then tune that model to understand the response of the wagon to that geometry. You can also tune different wagons, and effectively, once you run the geometry data, you can effectively run your model across it to give you an understanding of the condition of the track. So again, it's trying to bring in the frequency content, effectively the spatial content within each of those errors to give you the output or the response of the wagon. Certainly the EN's talking about it, ARIMA's talking about it, and we've actually got a project on the go at the moment in Indonesia. We're actually doing this exact piece of work. I'll have a slide on that in a moment. ARIMA, and Gary, you should probably be talking about this, and you may do later. I just touched on a few things. When looking at track geometry data, consider individual parameter thresholds, so peak errors, multiple thresholds, so where more than one defect exists in a region. Repeat defect analysis. Have we seen this location before? Do we need to prioritise alternative maintenance strategies? Well, I suspect a lot of people in the room have that latter problem. We'll send the tamper out there. Next week we'll send the tamper out there, so on and so forth. But the other thing they comment on, and they actually put a plot in there, is, and again, we've been talking about this today, we have, let's see if I turn this thing off. Track errors, sorry, track response, so that's wheel L on V up there, but there is no significant or geometry errors that are leading to that high response. Gary's just given us a whole bunch of examples of this. This is now being talked about in the ARIMA standard to say track geometry isn't necessarily the be-all and end-all of monitoring or assessing your track condition. Different forms of TQI. Don't know where we're going for time. Yeah. In the 2014 revision, the manual introduced the following statement. The goal of good track geometry is to ensure good vehicle performance or vehicle track interaction. Therefore, it is desirable to assess track geometry based on vehicle performance. Again, I don't think there's a lot of discussion as to how it's done. Gary, I'm happy if you comment, but it's certainly been noted that we need to start looking at alternatives. And we talk about the black box or the stuff that we were talking about just before, the frequency content of the data, using simulation models, your new cars, etc., or the use of instrumented wagons. I guess one of the limitations of the first two is that if you're using new cars or Vampire or these to assess different rolling stock, you need the base input for the simulation to run on. Now, if that simulation is only being run on data from a track recording car once every 4 months, is it good enough? So we therefore need to potentially get better ways of getting the data so that it can start to feed into a new car's, or, as we'll argue perhaps a bit later, go out there. Let's forget about understanding the transfer function, which is effectively a UM or simulation model. Let's just measure the response of the wagon and use that as your input to your track condition or your assessment of track condition. Some of the things that you can argue about geometry data. Often a track TQI parameter, well, I mean, there's some fundamental ones. TQI parameters often will give an equal weighting to things like gauge, surface. Are they really all of them as important as others in developing a TQI? Now, you can do better, and we make a comment in terms of weighted TQIs, using frequency content to define a track quality index. I don't necessarily want to run through all of these, but you know, there are limitations, and I think we probably all accept them. Have they provided the railway industry with a great tool over many years to provide a lot of good data? Absolutely, no question about it. There's a lot of models around, and well, I'm not going to spend any time really about talking about the different models and the pros and cons, but simulation models are geometry data is really accurate at telling you where the rail is. Shoving a vehicle model on top of it allows you to understand exactly what's going on with a whole range of different classes of rolling stock. Again, though, you know, we all use them. They allow us to do derailment investigations, assess track qualities. They're still limited by the frequency with which we get the track geometry data back into the model. But you know, they're a very powerful research and research tool. You can run 20 different classes of rolling stock over the same piece of track. So you've got your high-speed passenger and your coal wagons, and so you've got all the right cants in there, supers in there, and so a very powerful tool. This is the one that we were talking about before, predictive modelling. So you actually measure track geometries together with the rolling stock response, develop and validate predictive models to determine the response of the rolling stock to various track conditions. Let's say one of our chaps here is actually doing a lot of work in this area at the moment. But what it means is that you can effectively put one class of wagon out there recording data, so having one instrumented wagon out there, it will measure the condition of the track. You can then tune your algorithms for all of the different classes of rolling stock that are running on it to understand how they are likewise going to perform over those same sections of track. And as I say, we're actually doing this work under a grant arrangement between the Australian and Indonesian governments in Surabaya, is it, I think, and on their track there, and we've recently been over doing some instrumentation, and we're going back to permanently set up some instrumentation and further develop these models. So again, it's another way of you know, we talk about the fact that we're going to run multiple different wagon types on the different pieces of track, and then we say, well, that means we need 10 instrumented wagons or 20 instrumented wagons. Well, if we can set up the instrumentation on one wagon that can then be continuously monitoring and then feed that into other classes of rolling stock, that becomes an incredibly powerful tool in our view. Okay. That's sort of a bit of history in terms of and track geometry. I now want to introduce the where we've been going for the last 15 years in terms of new technologies, sorry, I'll use that term, for assessing track condition. Now, the background to the work that we started in 2002 probably started in about 1980, because one of the things as part of the R&D program for many, many years, we would always be going out there and temporarily instrumenting up wagons to try and understand what was going on, you know, hunting at different speeds. Can we take the train faster? Can we put more ore in the wagons? Can we pull a train over the hill? Or what's the in-train forces? But the problem up until 2002 that it was really hard to do on a long-term basis. Yeah, you would go up there and you'd have people sitting in the back of the wagons trying to start a data taker and hope to God that it got to the mine at the right time, and you know, it wouldn't run out of batteries or fall out when it was being rotary dumped. Or you know, there was a lot of challenges about turning that into a continuous system. 2002, we were talking to the railroad manager at BHP, and he said, "Why not have a crack at setting one of these things up permanently?" And because communications had improved, batteries had improved, power generation had improved, data logging had improved. So 2002, we started to develop the first of the instrumented wagons. But it was built around our knowledge of what was going to be valuable to the business. It wasn't some speculative thing. We understood what the railroad actually wanted and needed, or we felt we did anyway. And I guess we are where we are today with about 85 of these things having been built. I suppose before I go into this, and I know lunch will be here in a few minutes, I guess was there any sort of discussion or commentary or that people wanted to raise about track geometry data and whether I've done it a total disservice, or any thoughts or better ways of going about things? Yes?
I'm just wondering whether you believe that you've totally solved the issue of taking your measured data of the... Thank you. You've obviously got a very good measured data situation. When I look at those models like Vampire or Universal Mechanism, you've got to put in all of the vehicle parameters in terms of the vehicle.
Yeah.
Friction coefficients and all sorts of things. Do you believe you've nailed the ability to turn your actual vehicle dynamic information into reliable values in those models? Have you nailed it?
Probably not. I suppose one of the things that we're doing in terms of the simplified model, the AIC model, is that we're actually measuring the response of the wagons and more or less correlating that with the geometry. So we're sort of not caring about how the response is coming about. We're more trying to understand the response. And, Natushan, if you want to comment, you can. It's that, it's again using that effectively as the transfer function between the two sets of data. We're reasonably confident too in terms of a lot of the UM models that we've developed. We have validated against the instrumented wagon data, so we can use that to tune. Have we done enough of it in terms of taking track geometry data, running a Vampire and making sure that it's similar to the measured data is the same as simulated data? Probably not enough of it's been done, but we think we're probably pretty close. I mean, we're doing this stuff, the simulation modelling we've been doing since the late 70s, early 80s, and so we do have a very good understanding, I think, of the way the different components interact, friction wedge details, all of that, you know. So I feel pretty comfortable that we may not be the best in the world, but we're going to be not far away from it. Are there any other... John?
You mentioned the paper that you presented in 1986 about this condition model, and you asked why did it fail when I think everyone recognised that there was no fault in it. It was correct.
Oh, no, there are plenty of faults in it, but I'm not going to tell you.
No, but I mean, no one has claimed that it's fundamentally wrong.
No.
But it's in many cases, maybe Queensland outstanding. It actually has failed, and you asked why? Why did it fail? part of why it fails is that we so quickly fall into firefighting. When we collect data that is perfectly capable for